In this video, we are going to build a boilerplate for a Go-based backend, and we'll try to make it production grade. And by production grade, I mean we'll try to include all the modules that a serious or a production grade backend usually implements, and we'll implement all of those. And by boilerplate, I mean we will do this one time, all the setups, all the project setups, for example, the config setups, the logging setups, all the things that show up in every single project. We'll build all of those. That's called a boilerplate. We'll build all of those and we'll create a GitHub repo and I'll push it there. And from the next time on, when we start building projects, we will use the boilerplate and that will be our starting point. Instead of doing the whole project setup for every project, we'll establish the starting point in this video, and that will significantly speed up all our future videos. Now, the topics that we will be covering is something that I have mentioned in my backend from first principles playlist. This is the backend from first principles playlist. This is a separate playlist from this one, the Go based. And here in the backend playlist, we talk about all the theoretical concepts that a backend engineer should know to work on a serious production grade project, a backend project. The aim is to implement all those concepts in this boilerplate. For example, the routing layer, the serialization and deserialization layer, the authentication, authorization, the validation, transformations, middlewares, the request context, handlers, services, repository layers, the logging, monitoring, observability, graceful shutdown, and a lot of things. Pretty much all the things that you will need if you are working from a project which is like a small scale or a medium scale or a large scale. This is a very good starting point that we are going to establish today. And coming back to our tech stack, the major tech stack for the backend framework that we are going to use is Echo. Now, again, I have brought up this point a lot of times in especially the Go videos, that in the Go community, there is a lot of push to use standard library for everything. And that's how I started creating this boilerplate using standard library. And that module was complete. There was a lot of extra code and I did not feel like explaining all that code to a beginner. I did not have enough justifications for that. Echo as a framework is pretty lightweight as compared to something like Gin, which is another framework. And it does not try to abstract away a lot of things, just a routing layer and some parts of the validation layer. And it reduces a lot of code that way. So I feel using a framework like Echo makes a lot of sense, especially if you're starting out. And even if you're not starting out, you are an experienced engineer, there is nothing wrong with going with a framework like Echo. This is going to be the framework that we use. The second major thing is going to be the database driver. We'll be using PGX. This is a Postgres driver. By the way, we'll be using Postgres as a database. Of course, there are a lot of choices for other database. We could go with MongoDB, MySQL, etc. But Postgres is something which is pretty versatile and I've been using it for years, and it makes a lot of sense for most kind of projects. We'll be using Postgres as the database and PGX as the database driver. We will not be using any kind of ORMs. We will write raw SQL, but I'll show that writing raw SQL is not that bad, especially with our whole PGX based setup. And next up, for logging, we will be using Zerolog. Zerolog is a logging library, even though in the modern Go versions, we have Slog, which is a native standard library replacement for all these other logging libraries. But logging libraries like Zerolog or Zap or Logrus, these have been around for a long time. And because of that, there are a lot of integrations with other tools in the ecosystem, very good integrations. For example, Zerolog and PGX has a very good integration for logging our database based metrics, traces, and any kind of debugging data. And the same way, Zerolog also has good integration with the observability framework that we'll be using, which is New Relic. So using a separate logging library makes a lot of sense, even though standard library is more than capable. But because of the ecosystem benefits, we'll be going with Zerolog. For validations, we'll be using Validator, Playground, and this library. This has very good utility functions for doing some common validations across our handler layer. Again, even though we can write the validation logic ourselves, but that does not really make any sense. We already have tried and tested libraries which have been around for a lot of times. So we'll be going with this library for our validation needs. For config management, we'll be using this library called Koanf, which is a lightweight alternative to something like Viper. If you search for Viper, this is a very good config management library in the Go ecosystem, but it is also pretty heavy in my opinion, because it provides a lot of flexibility, a lot of features, a lot of integrations with other tools. And most of the time we don't really need that, especially if you are working in application code, creating your own backend application. Something lightweight makes more sense as compared to something like Viper. But if you're building something heavier, let's say a library or a application with a lot of integrations, things like that, then you can consider Viper. But for our use case, something like Koanf makes a lot of sense. And the reason for using a library for config management is they provide a lot of nice utilities for merging different configs with priorities and prefixes, etc., etc. So again, reducing a lot of code that we'll have to write ourselves. But it's not a very critical part, even though it is a critical part, but it is not a part which we will be dealing with on a day-to-day basis or every day. That's why delegating this whole code to an external library makes a lot of sense. Same way, if you apply the logic for ORMs also provide a lot of abstractions. But the reason we are not going with ORMs is because dealing with databases, writing queries and dealing with data is something which you will do 90% of the time as a backend engineer, as compared to dealing with configs, dealing with validations, dealing with these JSON parsing, JSON sending, all this logic. This is one time. You write it once, and maybe if you find a bug in the future about any of these modules, you make a change here and there, but that's all about it. You don't really deal with all these modules on a day-to-day basis. But data, databases, queries, etc., you work with it all the time. That's why we're not abstracting that part of our project to a library. We are writing the queries ourselves. That's at least my reasoning behind whether to choose a library or whether to go with our own implementation. Now moving on, for database migrations, we will be using this library called Tern. It is pretty lightweight, 1 or 2 files. This comes from the same creator who has created PGX. So they have very good integration, even though you can go with other migration libraries like Goose and Golang Migrator. There are other libraries, and pretty much all of them do the same thing, and there are no issues. Since it comes from the same creator, we went with Tern. Then for our tests, we will be using Testify. This library provides a lot of useful functions when we are writing our tests. We will be writing tests, at least some kind of unit integration tests for our application. So we'll be using this one for a lot of useful functions. And we will also use Testcontainers. This is another library which is very useful if you are running integration tests against your database. So instead of mocking, I'm not a big fan of mocking services, especially mocking databases. It's pretty useless in my opinion. Mocking has its place, but for a backend application where databases are pretty much the major part of your functionality, mocking databases is not the way we should be going around. So we'll be using this library called Testcontainers, which abstracts on top of Docker. So when we actually want to test our repository functions, our databases, queries, etc., etc., using this library, it will spin up new Docker containers, and it will provide a lot of utility functions to close the container, to start new containers, and provide a lot of pre-filled data. That's pretty much all our tech stack for the whole boilerplate. Let's get started with our boilerplate. Go to create a new folder called, let's say, go boilerplate. Let's open this in cursor. Great. Now we have an empty canvas. Now we'll be using a monorepo, and I'll explain why we are using a monorepo towards the end of this boilerplate video, because I actually have to show the use case why we are doing it. But in one line, if I have to answer it, we want to make use of some of the tools from the TypeScript ecosystem, tools like Zod and TS-REST for our OpenAPI contract, and for providing a type-safe client if we build a front-end application. So for those use cases, we will be using a monorepo so that we can keep our backend, all our packages, all our front end in a single GitHub repository. So we'll create a folder first for backend, and then there will be another folder for packages. Here we'll keep our Zod, OpenAPI, all the other packages. Now at the root of this, we actually want a package.json because we are making this a monorepo, and we want to run some scripts at the same time, and we want to make use of some of the utilities for that. So we'll just npm, let me just do npm init y, and we have an empty package.json. So the name is fine. Let's go boilerplate. We don't really need the main keywords. We don't need author. We don't need. Since this is a monorepo, we will need some of the keys to manage that. So I'll just add that here. We can go ahead and remove these because we are not really making use of all these features for managing the package. Now we'll be using Bun as a package manager. So if you don't have it installed, you can follow any installation guide for Bun. And the node version is at least 22. And if you are working on a monorepo, we have something called workspaces, and depending on which package manager that you're using, npm, pnpm, or Bun, they all have different places to keep this config. If you are using pnpm, then you'll have to create a file called pnpm workspace. But for Bun, we can keep it in the package.json. And we'll also need some scripts that I have. Just paste here. And these are scripts which, if we run in the root folder, which is the parent folder which contains backend and other packages, if we run these scripts, let's say we run lint or format, then what it will do, it will go through all the packages listed in our packages folder, which we don't have now, but we'll have later on. And if we also have a front-end app, then it will also go through the front-end app, and it will run the script for formatting the front-end app. We won't be using it for now, but we just add it here in case we need it in the future. And in case you are not familiar with the JavaScript ecosystem, the TypeScript ecosystem, the front-end side of it, then that's also fine. We are not going too much deep into that part of the ecosystem, but only some of the essentials that we'll be needing. After this, let's install two packages. I already have Bun installed, so I can run these commands. So we'll add Bun, add, and D. We'll need Turbo with Turbo repo for managing our monorepo, and we'll also need TypeScript. These two are installed here in dev dependencies, and we also created a bun.the log file. Another thing that we'll need is a turbo.json for managing some of the tasks like formatting, linting, and starting the dev server or running a build script. And this is something you can get from the official documentation, which I have also copied from. Again, we'll not be using it here as of now. We'll use these towards the end of the boilerplate, but since we are building from scratch, I'll add it, whatever we need in the root folder. Another thing that we'll need is a git ignore, so that we can add a few files, folders, which should not go into version control. So the name here is go boilerplate. And I am adding this one here because since the name of our project is go boilerplate, when we actually build the project, it will create a binary, an executable binary, and the name will be Go boilerplate. That's why I'm adding it here so that we accidentally don't push that into our version control. That's all about git ignore. And the last thing that we need is a readme file. Right. readme.empty. For now, we'll just write go. That's fine. We don't need to add more information for now. We'll come back to this later. That's all about the root folder, everything that we need to add here. Now we can jump into actual Go backend. And for the backend, we will be following the standard project structure. We search Go standard project layout. We'll find this GitHub repository, and it gives you some of the not rules exactly, but some references about how you can exactly structure your Go backend or any kind of Go application, not necessarily limited to your backend. It can be a CLI also or a library also. I have not strictly created the project structure according to this, but will be following most of the rules. So going back, the first folder that we'll need inside this is CMD, and inside CMD, we'll create another one and the name will be Go boilerplate. Usually the idea is inside CMD, we'll keep the main file, the file which actually starts your server, and that will in turn create the executable that we will use later. Inside CMD, the folder we create, we named it Go boilerplate because the name of our project is Go boilerplate. So that is another pattern you can follow. And inside this, there will be a main.go file, but we'll come to that later on. Then again, inside backend, we'll create another folder called internal, and internal will contain pretty much all the logic related to our application, everything, the routing, the handlers, services, repository, database, configs, loggers, everything. We will also create a .env, and we will store all our environment variables inside .env, and we'll also need a sample because the .env we are not exactly pushing to Git. Inside sample, we can document what are the variables that we are using so that if someone new joins your project, they can refer to this file and add all those variables. Then again, we'll create another git ignore, and this particular git ignore is for our Go application. The one that we created in the root is for mostly the TypeScript ecosystem and also some of the Go files, but just to be safe, we are creating another git ignore file so that we can keep it limited to all the Go specific outputs and Go specific things that we want to ignore from Git. Then we also want to create a file for linting our project, and this will be golang ci.yaml, and this is the content. Linting is optional, I would say, but since we are going with a production grade project, linting is something we should try to implement. We'll not try to stick to it very strictly, but we'll just keep it here just to complete the boilerplate. But of course, you can go ahead and run lintings and fix all the lint errors if you have enough time. And we don't need to understand all the different configs, what all of them do. I have copied it from the official documentation. There is a section on recommended settings, and there are also a lot of GitHub repositories where people have recommended that these settings work better. So not something even I don't understand pretty much all of them. I know what some of them do, but not important. Then we'll again create another readme file, which will have information about our backend, not the whole project. For now, we'll just add it here. And the last thing that we need to do is make this backend folder a Go module so that we can install different libraries, and this whole folder, just the backend folder, will behave as a Go module. Let's just cd into the backend, and this is the command you can try, go mod init, and the practice says you have to prefix your project name with whatever version control that you use. So in our case, it is github.com, and my username / the name of the project says Go boilerplate. And when you run this, it creates a go.mod file with the current version of Go that is installed in your system. By the way, if you are working on this, I am assuming that you already have Go installed in your system. We'll not be going very basic into explaining every single thing, assuming you have done your research, not the first time you're hearing about all these terms. Now that we have our go.mod file, we can install different packages, libraries in our project. Now, the last thing that we need in the root of our backend is a task file dot YAML. Now, if we look up what is task file is basically a tool for executing different commands and different workflows. It is a alternative to make. Make is very famous for these kinds of stuff. You must have already used it if you have worked in the Go ecosystem or C programming and other ecosystems. But task file, it provides a cleaner syntax and it is a modern alternative to make. There are not a lot of differences, but I felt that the syntax of task file is a little lighter. It does not contain a lot of concepts that we don't really use on a day-to-day basis. So instead of make, we are using task file. And the reason we are using it because every time we want to execute something, let's say we want to run our server, then we have to do something like go run and cmd, then the name of the project, then go, something like this. We want to abstract this out. We want to make this a shortcut. So we can just say that just run task run, then it will start our server. So that's the reason we are using task file and a lot of other commands related to databases and running our linting, testing things and those things. So the content of task file is going to be this. I'll just explain briefly because there is not a lot of deep syntax here. You can go through the official documentation once, but you don't really need to. You can just copy and paste this file in your project and use it forever. I have created it once and never even made any change in this. So not something you have to put more effort into learning. Also, you can consult things like LLMs, Claude and ChatGPT to help you out in this. So just to explain what's happening here, we are creating a variable here. Select this Alfred. Instead of Alfred, I'll make it boilerplate dbdsn. And again, let me search for Alfred. This is also go boilerplate. Then here also we have to change. And one more reference, you can just copy paste here. Great. So what's happening here is we are creating a variable and we are saying we'll be reading this variable from environment, from your operating system's environment variable. And we are creating a couple of tasks. These are the workflows we are declaring. The first one is help, which basically prints out all these tasks and how to run them and information surrounding them. Then second is a utility for confirming whether you want to proceed with a task or not. For example, for things like applying database migrations, which is a sensitive task, is something a lot of things can break because of that. That's why we are adding a confirmation there that are you sure you want to run this command? So this is a utility which we can use for other tasks. Same way, we are using this task called run, which basically runs this command, go run and our whole project. So it will start our server. For migrations new, it uses this command line utility called Tern, which is a database migration tool. And it goes to this folder. It creates a new migration file with a new serial number. And we can write our SQL migrations inside that. Same way, the migration up command, this is for the Tern command line utility to go inside our migrations folder, whatever files that we have created inside migrations, and it will apply all those SQL statements on our database. Okay. So if we did not have this, where we can just write task migrations up, we would have to write all these things every time we wanted to up all our migrations, apply all our migrations. That is the reason we are using this task file. Same way, we can just write task space tidy and it will run all these commands. It will format all the files in our project. It will run go mod tidy, which basically cleans up our go.mod file so that unused dependencies get deleted from our go.mod file and other verifications. That's pretty much all about our task file. When we are ready to run our server, we can just try task space run and it will start our server. And that's all the files that we will need in the root of our project. Now moving on, where should we start from? Let's start from the main file inside Go Boilerplate. We'll create the first file which is called main.go, and we want to name this as package main, because when we actually execute this file, we want to create an executable and we want to run this particular application. That's why we're naming it package main, because Go looks for a file which has package main so that it can generate an executable from that. And it will have a function called func main. We'll add more code in this later on, but just to show you that it works, let me just add a print statement and go back, clear this. Let's run our task, and you can see that we have hello world runs this particular command whenever we do task run, does go run cmd go boilerplate, and that's why we see the results. Okay. Now that we know our server is running successfully, not server yet, but our program, we can start configuring our backend. We'll come back to the main.go file in the end, because main.go, the whole purpose of main.go is initializing all the other services, all the other modules, and actually starting the server. So we'll have to build out all the other modules first before we come back to the main.go file. Okay, so the first thing, let's create all the folders that we'll need inside internal. The first one we'll need is config, and inside this we'll store all the logic related to our config management. And next one, database, for storing our database migrations, our database connection logic, etc. Next up, we have errors, for storing all our custom errors and error handling logic. Next up, we have handler, storing our handlers. Then we have lib. Now this is a folder which is just there so that we can store any other modules which does not really belong anywhere. It is kind of a library that we'll be using across our application. So if we come across any kind of logic like that, we'll keep it inside lib. Then we have log, is very important module which we'll be using everywhere in our application. Next, we have middlewares. We'll store all our middlewares here, the global middleware, error handling middlewares, the request ID middlewares, and every kind of middleware, and all the other middlewares. And model, this will contain all our Go structs, which has a one-to-one mapping to our database tables. And it will also contain all the DTOs. DTOs basically mean that what does the input structure looks like and what does the output looks like. Those are called DTOs, data transfer object, so that we have a structured way of dealing with what comes inside for an API method and what goes outside. Then we also have repository, where we will store all our database queries and different modules in our app. Then we have router, server. Server will contain the actual logic which spins up a new HTTP server, which we will call in the main.go file. Then we have service. Service is basically the second layer. The handlers deal with validations and passing whatever data the service needs. So that is the first layer. The second layer is service, which actually calls the repository methods, which is the unit level methods, and deals with all the business logic. So we'll keep all our services in this folder. Then we have another called SQL error. This will contain all the logic for handling different database errors. We also have testing, for keeping the common logic, the reusable logic that we'll be using for writing our tests. And we also have validation, for containing all our logic related to validations. We will also need, in the root of our application, we'll need a folder called static. This will contain OpenAPI.json file, which we'll be generating. We'll not be writing any OpenAPI contracts by hand. We'll be generating it, but static will contain it so that we can serve it and start a server and test out our APIs. So that's pretty much all the folders that we'll need. in our internal folder for keeping all our logic. So let's start with config. Let's create a file called config.go, and it automatically takes the package name as config. And inside this, we'll store all the Go structs, and we'll read whatever environment variables that we have from .env, and we'll store all those values inside Go structs, and we'll reuse it across the runtime of our application without reading from environment again and again. We'll read it once when the application starts inside main.go, and we'll reuse it everywhere. For this, we will need a struct, say name struct config. For now, we'll keep it empty, and we'll create other structs, the child structs, so that the primary struct, the parent one, the config struct, this stays clean, and we can neatly organize what particular struct deals with what part of our config. The first one is, let's say, primary. This is going to be a struct, and we want to keep the name of the environment here. The type is obviously going to be string, and we'll need some struct tags. In Go struct tags, these are called struct tags, whatever is inside the backticks. And in Go, struct tags play a very important role when it comes to reflection. Reflection is basically understanding the structure of a data during runtime, and using struct tags, it is one of the techniques using which we can add some metadata about a struct and use that during the runtime to perform some operations. So each library can define some kind of key using which we can pass some metadata. So since we are using this library called Koanf, using this particular tag, we can pass some data to this struct, which the library is able to parse and perform various operations. Same way, the validate tag is associated with the validator package that we'll be using for performing our validations. In primary, we'll just need one variable for keeping track of what is the environment that we are running in currently. The second one we'll need is the server config, and this will contain the port. What is the port that our server is going to be running on? Usually it's 8080. Then the read timeout, idle timeout. These are the timeout values. If you have a long running HTTP request, let's say you are running a image generation query using some kind of OpenAI API, and that request takes more than a minute, more than around 1.5 minutes, and you have configured your server timeout as 60 seconds. Then after 60 seconds, the request will end, and your client, whatever front-end client you're using, whether it is Postman, Insomnia, some kind of app, web app, you will get an error of 504 that request timed out. But if you have configured the timeout to be, let's say, 180 seconds, then the request will continue to run, and you will get the result on the client side. So timeout values are something we have to configure so that we are conscious about what exactly is the default timeout of our servers. And the last one is the allowed origin of CORS. A CORS is a mechanism which prevents web browsers to access resources from a different domain in a particular domain. Okay. You can get more information about how this whole CORS thing works in the HTTP video of Backend from First Principles. We'll not go too deep into that. But using this, we can pass an array of domains that we want to allow from server side. Usually we pass our front-end domain here so that we don't get CORS error when we are making some kind of API call. And the last one we need is the database config. Now these are some of the parameters that we'll need to connect to our database. This is the host, this is a port where your database is running on, then the username, the password, the name of the database, if SSL is enabled or disabled, a maximum number of open connections we are allowing, maximum number of idle connections, and some other parameters. Next up, we'll also need auth config for storing secret key. For this, I forgot to mention, but for authentication, we'll be using Clerk for the authentication provider. Even though I did start out with a completely manual authentication and authorization workflow, but again, I did not think it's productive for including all the different workflows and all the different concepts in a boilerplate video. It will take hours to explain, and a lot of people will face issues if they miss some kind of step, and getting authentication wrong is not a good thing, especially if you are building a production system. So we'll be using an authentication provider. So we'll be using an authentication provider for this boilerplate and pretty much all our future videos, so that we can actually focus on our business logic, our backend logic, instead of going too deep into the authentication and authorization domains. And now that we have all our different structs for different parts of our config, in the final one, we can use this. This parent struct now has 4 fields. One is primary, then server, database, and auth, and each have their own struct types, so that this parent struct can validate whether they exist or not. And then going one level deep, these structs in turn can validate all the fields that they contain. Okay. Now we have the final struct that we'll need for containing all our configs for our app. Then we'll need a function which actually takes all the environment variables and loads it in our config struct. So let's create a function called load config, and this will return a pointer and an error if there are. Now we're returning a pointer because we want to read all the variables into a struct, and we just want to pass it around the whole application. And even though the size of the struct is not big to be considering whether you should use pointers or not, but since it is a single reference that we want to maintain throughout our application, I feel going with a pointer makes more sense. First thing that we want to do is we want to create a logger, and we will use this logger to output some of the events that will be occurring while this function runs. Importing Zerolog, and we are creating a new logger, and this is a console writer, which basically means that whatever output that gets generated from this logger, it is going to get printed in our console here instead of any kind of other exporters like files or any external log providers. And then we are also including timestamp with the logs, and finally we are creating a new logger, and this logger is going to get stored inside this variable. Next up, we have to create a new instance of Koanf, and we import it and go mod tidy, and that should fix the error. Okay, now we are creating a new instance. Then what we want to do, we want to load our environment variables from the .env file, and we want to load it in our structs. So for that task, for loading from our .env, we need a package called go.env, and this package provides this function called autoload. At the start of this file, when this file actually starts getting executed, when it reaches this point, it will import this function, and this function in turn, let's say if I run go type, let's go ahead inside this function, and if we open the source code for this, we can see that it has an init function. And inside the init function, it is calling this go.env.load. Now, the init functions inside Go files have a special purpose. Every time you import a new file, the way we are importing it now, all the init functions inside that file will be run automatically. And because of that, the moment we are importing it, this, our variables inside .env, we don't have the variables yet, but all these variables are loaded inside our memory or inside our runtime environment. Next up, we are actually loading the environment variables. We have already the instance of Koanf inside this variable called k, and we are loading it, and we want to load it from a provider which is an env provider, which basically means that we want to take the variables which is already inside our runtime environment, and those variables, we are saying that they have a prefix called boilerplate. And prefixing environment variables is very useful, especially when you're deploying your application in servers, Linux servers, inside EC2 or any other kind of setup. And you also have other applications inside that server. If different applications start polluting the environment variables of a particular operating system, sometimes it becomes a problem overriding each other's values. So what we are doing, we are prefixing all our environment variables which we are going to load inside our operating system, and we are prefixing it with the name of our app. We will add all the variables here inside .env later on, but this is how we are loading it. We are trimming the prefix, which basically means we are cutting out this part, and whatever comes after that, we are taking that, we are converting it into lowercase, and then we are loading it inside our structs. So something like a capitalized prefixed variable will be converted to something like this, a lowercase snake cased format. Before this, I think I forgot to add another config, which is a struct which we need for managing our Redis instance. It will contain the URL of the Redis instance, and we also need to add it inside the main struct. Let me just add it here, not here. Let's add it here. Okay, now moving on, after we have successfully loaded environment variables inside this K instance, now that all our variables are inside this K instance, we'll just go ahead, create an instance of our config, the parent config, using this syntax. And what we'll do, whatever variables that we have loaded and stored inside this K variable, we'll try to marshal that inside our this struct, our parent struct, which contains other children structs, and they contain more fields in turn. And we load that inside the main config, all the values that we have read so far. After this, we should go ahead and validate if all the values that we have provided, they are present or not, if any value is missing or not. For this, we'll need this package called 10. We have to run go tidy, so adds the package and adds the checksum entry inside go.sum. We are creating a new validator instance, and we are validating this config, this main config, according to all these rules that we have added. We have only added this one rule which is required. This should be present. We are not drilling down on this should have these many characters and all the other conditions that we can add. We are keeping it simple. It should be present, and that's all it matters. If at this point the validation fails, then we are doing a log.fatal, and log.fatal basically means that our application is going to raise a panic, but it will raise a panic with a message that config validation failed. And if there are no errors, then we'll just go ahead and return main config, the error will be nil. And this is how we load all our configs from .env into our struct, which will be passing around throughout our application. And since we are already dealing with configs, let's just also add the config that we need for our observability setup. For that, we'll create another file because it contains a lot of logic, and we don't want to pollute this file with all the observability related configs. Go. The package will obviously be config since the folder name is config, and I'll just go ahead and paste the whole thing here, and then we can see what all we are doing it. Okay, now we have a struct which is again a parent struct, and it contains all the configs related to observability. Now, when we are actually using these configs, I'll be explaining what all these different variables, different fields actually do. But for now, let's focus on how we are actually loading the configs. Inside observability, we have a couple of fields. First is the service name, and inside this we'll write the name of our app. For this, we'll just pass boilerplate. Environment, what is the environment, whether it is local or whether it is production, right? The logging config, this is another struct. All the configs related to New Relic, the service provider that we are using for our observability needs. Pretty much all the logging, monitoring, and observability needs. All the configs related to that will be inside this. Then our health check configs will be inside another struct. Inside logging, we have three fields. What is the logging level that we want for this environment? For development, we'll keep this as a debug level, and for production, we'll make it as info level. And format, for development, we want the log formats in console, and in production, we want them in JSON. Then we have a slow query threshold. This is a parameter that I am not sure whether I'm using or not, but the whole point of adding this was we are obviously monitoring all the database queries, all the database executions throughout our application. And if for a particular database operation, the execution times crosses a particular duration, let's say usually we expect the execution time to be under 400 milliseconds. But if for some reason it exceeds 800 milliseconds, then we want to perform some operation. We want to log the event, and we can see that in our observability dashboard, in our new Relic dashboard. And that's how that's why I had added this variable. We'll see if we are using it or not. If we are not, then I'll just go ahead and remove that. Then we have a new Relic config service, which we'll use for all our logs, monitoring, and observability. It needs a couple of configs. One is the license key, of course, for initializing the service and using the service. Then a couple of flags to make sure we are forwarding the logs to the service. We are also forwarding the traces to the service. And if we want to log all the debug related details for New Relic. Usually we keep this disabled unless we are facing any kind of issue related to New Relic, so that we can dig down more. Then we have our health check related configs. What are the different things we want to keep in mind while we are running our health checks? We need health checks so that other services can constantly monitor whether our application, whether our server, whether our databases, whether our Redis instance, all these things are running normal or not. That's the use of health checks. We are creating a function which is called default config. If observability related data is not provided inside our .env file, then we are creating some default values. Let me change this to boilerplate. Environment is, we are keeping the default as development. Log level is info, format is JSON, threshold is 100 milliseconds. Then these are the new Relic related configs, and these are the health checks related configs. You want to check database and Redis for now. And as we add more services into our app, we'll also add more health checks here. Then we have a function here for actually validating our configs that we have from our environment. And we have a function here for getting the log level. So depending on our environment, whether we are running in production or development, we are changing the log level. So if it is a production level environment, then we are keeping the log level as info, and using this function, we can fetch that. And for development, we are keeping it as debug. Then another utility function that we are using to quickly check whether this environment is production or not. Great. That's all about our observability config, and we want to integrate that inside our main config. And the first thing that we want to do is embed that struct here. Now we have a pointer to this because all the configs related to logging, monitoring, and observability is optional. That's why we are using a pointer so that we can differentiate whether it is a 0 value or it is a null value. If it is not provided, a 0 value for a pointer will be nil, and that's how we can check whether it is provided or not. And we also have to initialize it here. So let me just add it. Before we return, we add this checks related to observability. We're checking if observability related configs are passed or not. If they are not passed, we are creating a default struct using this function. It returns this struct, and we are setting the main config observability value to this. If it is passed, then service name we are setting manually, which is boilerplate. Environment we are taking from our primary environment from here, whether it is production or local or development. Then finally, we are validating it according to some rules. This is our validation rules, and after that, as usual, we are returning the main config. And this is pretty much all about configs. We'll not be touching this part as often. It is just a one-time effort so that we are following all the best practices when it comes to loading configs inside a backend system. All this code is of course going in a GitHub repository, so in case you miss something, no need to worry. You can directly refer to the repository that will be in GitHub to cross check if you missed something or did something wrong. And the reason I'm not typing out everything, and the reason I kept everything prepared before this video is the obvious reason is, of course, it's going to take a lot of time typing out everything, time which can be better utilized creating more projects which deal with actual businesses, actual ideas, and more technologies instead of focusing more on syntax. The whole reason I am making this video about how I created this boilerplate, and I have created this boilerplate not like overnight or within a few days. I've been working with Go for the last 3 years, and this is the boilerplate that has come out of all the experience in the last 3 years, the professional experience and the freelancing projects and the personal. I have noticed some patterns. I have noted down patterns from open source repositories. This is the boilerplate or a project structure that I use in my personal project, professional projects, freelancing projects, everywhere. And this repository is actually meant to be cloned and get started with instantly with whatever business logic you have, whatever app idea you are building, whatever backend idea you are building. But I made this video so that you're familiar with the different parts of the project and the thoughts, the reasoning behind why we are structuring certain things in a particular way, why we are creating a particular file, why we are writing a particular line of code, and everything. Even though you're not typing it out, as long as you understand my reasoning behind why we did something, that's more than enough. Eventually, when we build projects, 1, 2, 3, 5, even more projects, every time using the same boilerplate, every time going through the same pieces of codes again and again, you'll get the hang of it. Even though some of the concepts, some of the patterns that I am doing now is not as clear as you would like it to be, but as you're building more using the boilerplate, using this particular structure, you'll be very familiar with all the different components, and whatever doubts you have about different things, they'll all go away eventually, right? So if you are feeling a little lost, then that's okay. That's not something I did not see coming. It's pretty normal. So just try to watch this video. If you want to follow along, write the code, type it out yourself, then that's great. But even if that seems overwhelming, just try to watch this video, understand whatever and however much as possible, keeping the syntax aside. Try to understand the patterns, why we are doing certain things and how we are doing it. Don't worry too much about the syntax. As we write more code, that will become second nature. Okay, with that, let's jump into the next module. We'll write the logic for database connection, database migration, right? We'll need a file inside our database folder. So let's create a file called database.go. The package is, of course, database because the folder name is database. And inside this, we'll have the logic for connecting to our database. And if you have watched the database video in the backend from first principle series, then you'll know about this concept called pooling, database pooling. So pooling is basically a technique using which a certain number of connections will be open from our backend, from the process that is running our backend to the database process. Database is also considered one type of backend. So our backend connects to our database server using the TCP protocol. And if we use pooling, a certain number of connections will be active and our backend is going to maintain them over time. Instead of every time we get a new request, creating a whole new connection, making the TCP handshake and going through all the different technicalities. By keeping a certain number of connections in hand, our app is going to be more efficient. That's the whole idea of database pooling. So what we need first is a struct, a data structure where we can store a couple of things, and we need two things for our database. So let's create a struct called database struct. First, what we need is a pool. We want to store a database pool, and it is going to be a type of pool.pool. And the second thing we need is a logger, because of course, when we are trying to establish connection with our database, we want to log some things, and we are using Zerolog for that. So it is going to come from Zerolog logger. Now we have two things. Let's clear these errors with go mod tidy. Next up, we'll create a variable for the database connection timeout. Every time we want to create a connection to our database, we want to keep a timeout of 10 seconds, so that if it exceeds that duration, then we will stop trying and we'll report that there is something wrong. So let's create that variable called database ping time of 10. Now our database connection logic has a dependency on our logger. Since we have not created our logger, I think we should pause here and first create our logger, then come back and finish this part. So let's create a new file called logger.go, and here we'll add all the logic related to our logging. Now this has a lot of moving parts, because when we are talking about logging, it indirectly also includes two other aspects. One is monitoring and other is observability. For observability, we are using this service called New Relic, and it offers SDKs and different tools so that we can properly instrument different parts of our application. And when I say different parts, we'll be instrumenting our database, whatever database logic we have. Then we'll be instrumenting the core part, the request logger, which is the middleware, which is going to keep track of all our requests. When we instrument that part of our code base, we can cover a lot of scope when it comes to logging, monitoring, and observability. Now, given that there is a lot of configuration involved in this file related to all three aspects: logging, monitoring, and observability. So it might seem a little overwhelming, but just bear with me. I'll try to explain as much as possible. The first thing that we want to create is a new Relic service, which is going to be a logging, monitoring, and observability provider. And it comes from this package. And we are storing an instance of that application in a struct called logger service. Now we need some way so that we can initialize this service, which is the logger service. So we'll create a function called new logger service, which will take our observability config, whichever the config that we added here, and it will return a new logger service using that config. So this is what the signature of the function is going to look like. We are taking a observability config instance, an instance of this config struct, and we are returning a pointer to this logger service that will initialize in this function. So first, let's just create an instance of this struct, which is the logger service, and inside this variable service. And here we have to check if we have the license key provided or not. For using New Relic, we'll need a key, which you will get when you register in the service. You can follow the official documentation for how to register and get your key for New Relic. Here what we are doing, we are checking from the provided config if we have the license key or not. If we don't have a license key, we'll just return an empty service without initializing the observability related stuff. But if we have the license key, then we'll continue. And to initialize the service of New Relic, we need a couple of parameters to pass. For that, we'll create a new slice, which is of type new relic.config option. And this is a variable, and we are appending all these 4 different configs inside this config option slice. First thing is the service name. In the service name which we added, which is the name Boilerplate. Second is the license key that we have in our environment variable, that which we will add later. Then we are saying we want to forward our logs to New Relic. And the fourth one is we also want to forward our traces. Traces is basically a transaction starting from one point of your system. It can be your front end, it can be your load balancer, or it can also be your backend middleware. And it starts from that point, it passes through handlers, it passes through services and repository depending on your configuration. So that complete interaction is called a trace, and it helps us debug things. You can watch the logging, monitoring, observability video in the backend from first principles series to understand more about that stuff. After that, if the config debug is enabled for New Relic specifically, then we also want to append another config, which is the debug logger. This we are disabling both for local and production environments, but if we face any issues related to New Relic, then we can enable it to debug things further. If all the config stuff works properly, at last we'll just initialize the app. Here we are creating a new application from the library provided by New Relic with all the config options. This ... is basically a spread operator. It will take a slice and it will pass all the elements of that slice as arguments into this function one by one. If we face any error, if error is not nil, then we'll say fail to initialize New Relic and we'll just return the empty service. But if there are no errors, then we just insert the newly created app that we got from here inside this nr app field that we have inside logger service. Then at last we return that service. We just add a print statement just to give some info that we were able to successfully initialize the logger service. After this, we want to create a method on the logger service, which is the shutdown method, and we will call it when we are gracefully shutting down a backend app. We'll get to the graceful shutdown implementation part, but all different modules in our app will have their own shutdown logic. And in our central graceful shutdown logic, we'll call all these functions so that we have a clean shutdown. All the services are given enough time so that they can clean up resources, they can drop requests and whatever they have to do for shutting down. And then we finally shut down the main process, the main go routine. For that, we'll create a receiver function on top of the logger service so that we can directly call the shutdown on that. If there is a New Relic app, then we call the shutdown method on that. And that's how we shut down the logger service. Then we are also creating a utility function so that if we want to access the application inside this, which is the nr app. One thing about Go is if a struct has a field and its first letter is not capital, then we cannot access it outside of the package. And because of that, we have created a function, a utility function, is a receiver, and it will take the logger service implicitly and it will return the nr app, which is not exposed outside the package, but using this getter. If you are familiar with other programming languages terminologies, then this is kind of a getter. Finally, we get to the part we actually create a logger which we will be using across our application. It takes two parameters. One is the log level, and second is if this environment is production or not. And it returns an instance of a Zerolog logger. The type is Zerolog logger. And this is just an initialization function of a new logger with service, which we'll write down after this. But since that's a long function, I just wanted to show the parent function first, the initializer function. And it takes an instance of the observability config and it passes the appropriate values. If it is prod, then we pass production, otherwise we pass development, and it returns a zerolog.logger. After that, we have another utility function here to pass the config and get a new service. And finally, this is our function, which is going to actually return the logger by performing a couple of steps. It will take an instance of the observability config and the logger service that we created here, the new logger service, which is related to the New Relic logger service, not our application logger. First, we are creating a new variable called log level, and we are using this utility function that we had created earlier to get the current log level. If it is production, then we are returning info level. If it is development, then we are returning the debug level. Then we are just taking the string and converting it to the appropriate type of zerolog.level. If it is debug, then it is debug level. Same for info, warn, and error. Then this is the format of the time that you want to display the logs in. And this is for displaying stacks, error stacks. If you get some error stacks, then using this, we can show the stacks. Then we are creating a variable of this interface. io.writer is an interface, and we are creating a new variable of this type. And this particular section snippet basically deals with whether we should forward our logs to New Relic or not. if it is production and if the log format is JSON, then we are going ahead and forwarding all logs to New Relic. Otherwise, if it is not both of these things, then we are in development mode and we are just initializing a console writer, and that's what we are assigning to the writer interface. Console writer basically means that whatever logs that we have, it will be displayed in the terminal instead of in a file or sending to an external service. And finally, we take this writer with all the configs of New Relic and the console writer, and we create a new instance of zerolog.logger. We pass the writer inside new. The level we set as log level, whatever we had decided. For development, it will be debug. For production, it will be info, with timestamp structure that we have decided here. The service name, which will be boilerplate in this case, but you can give it the name of your app. Then the environment, whether it is local or production, and finally return a logger with all these configs and store it inside this logger variable. Here we are saying that if it is not production, then we want to get the stack of an error. If it is production, then you can just ignore it. And finally, we are returning a logger. This particular function, new logger with service, this gives us a logger with New Relic configs already configured. Right? That's the whole purpose of this function. After this, we also need a couple of utility functions that we are going to use a little later. We'll just go ahead and create it now. The first one is for adding trace context. Now this function with trace context, it takes a Zerolog logger instance and a transaction which comes from New Relic. In New Relic, a transaction is basically, as I said, it's kind of like a trace. It has a starting point and it has an ending point, and all the interactions, all the components it touches during the whole request lifecycle, all of them are included in a single transaction, so that if anything goes wrong, if you are trying to debug something, then you can take a particular transaction and you can explore what are all the functions it passed through and what are all the components it touched. That's the whole purpose of a transaction. We'll see how we are going to use transaction later, but that's a high level definition of transactions. And here we are checking that if a transaction is not already created, since it is a pointer, we can check that if it is nil, then just return the logger without doing anything with the transaction. But if it is not nil, then we are calling this function which is get trace metadata. Trace metadata is basically a function provided by New Relic itself, and it provides us two things. One is a trace ID and one is a span ID. These two things, if you are familiar with telemetry or instrumentation, these two are important in that context. But just to simplify things, these are parameters which New Relic or any kind of instrumentation service uses to connect all the components a particular transaction passes through. Right? That's the use of trace ID and span ID. And so next, we will be integrating our Zerolog logger with our database driver, which is PGX. We'll get to that part soon after this, but we'll be integrating our logger with our database driver so that during our development, we can get some data about what are the database queries that we are executing. So it will print the SQL query that our database driver finally executed and all the parameters that went into that query. And if you're familiar with how database queries and etc. work in backend application, we use this concept called named parameters or positional parameters, basically parameters in database query, so that we can avoid security risk like SQL injection, which happens when you take user input and you just string concatenate them with the SQL query. But if you use parameters, then a statement is already prepared beforehand and that parameter will be inserted as a string without giving any kind of execution capabilities. So coming back to the point, since we want to log various things in our database driver, we have to create some utility functions for that. Then we need a separate logger for database driver so that we can appropriately print different things like SQL queries, arguments, how much latency a particular database query took, things like that. And we can do that using this function. This is a function named new PGX logger. PGX is the name of our database driver. It takes a log level, whichever level we want, and it returns again a zerolog.logger type. We instantiate it using a zerolog.console writer We are using console writer because we need this in our development environment, because in our production environment we are setting up a database tracer. New Relic provides us a very good integration with the PGX driver, so that in production all your database queries and the instrumentation data about them, data like the SQL query that was executed, the arguments that was passed to it, and how much time it took, and everything surrounding it, all of that will be recorded by New Relic and we can see it in the dashboard. But in development environment, we are not sending that to New Relic and we are just printing it in console. We are instantiating a new console writer which comes from Zerolog. We are saying that we want to print it in our terminal. That's what std out means, that is standard output. This is the time format that we want our timestamps in. Then we are passing a function in format field value. How do we want to format different fields for this particular database logger? We are just switching over the type of whatever we have passed here. If the field type is a string, then in that case, we know that it is the SQL string that was finally executed, and we are just truncating it to 200 characters, because in some SQL queries it can get very long if you have very complex joins across multiple tables, 10s and 15 tables. That's why we are truncating it so that we don't overwhelm our terminal and it becomes very difficult to make sense of what's happening. Then if it is of type byte slice, this is called the slice of byte, then we know that it is the arguments. For that, what we are doing, we are just trying to unmarshal that as a JSON and indent it properly so that we can make it more readable. If it's neither of these, then we are just returning the string. And finally, we take this writer that we just created and we create a new Zerolog logger instance with this as the writer. Since this console writer is also of interface io.writer, we can just pass it inside the new, and we set the level with timestamp and the component. We are saying that the component that we are currently logging in is database. Then we are just returning that logger. And finally, one last function that we need for database logging is get pgx trace log level. Basically, it takes a Zerolog level type, and depending on the type, it converts that to appropriate trace log. I'll explain what it means when we get to the database part. Basically, for debug, it's returning 6, 4, 3, 2, and by default it is of 0. And that's all the configurations that we need. Logger, including New Relic configs, application logger, and database logger. So to get rid of these errors, I'll just run go mod tidy once, and the errors are gone. Now that we have our logger ready, we can go back to our database and finish the integration. Now here also we'll have to configure some of the New Relic integration. Logging, monitoring, and observability is very important, especially in a production system. If there is one element that you want to say which distinguishes from a hobby project to a production project, then this is that, which is how serious you are taking the whole logging, monitoring, and observability scene. Since I'm claiming that this is a production grade boilerplate, then I want to take this seriously. I want to add the observability part to every component in our code base. And since we are using New Relic, it has very good integration support for PGX also. Now in this module, in this particular file, we'll also integrate the logger, the development logger that we created just here, the new PGX logger using this is for our development environment. And we'll also cater to our production environment by integrating New Relic for our database related traces, database related metrics. For that, we need a couple of functions, receiver functions and utility functions. The first one we need is a struct for keeping track of all the tracers that we are integrating into our database driver. Since we are using both development tracer and a production tracer using New Relic, we are creating a new struct which is going to have a field called tracers, which is going to take a slice of any type. Now on this tracer, multi-tracer, we will create two receiver functions. so that we can manually trigger the tracing part for both our development tracer and production tracer using the new Relic part. I will create two functions. One is trace query start and the second is trace query end. This will be triggered when the whole transaction, the whole trace starts, and this is when we are returning from the function. They'll take a couple of things. One is the context. Go has this feature called context. So you can think of context as some kind of memory, some kind of storage, which can contain all the information for a particular request, starting from the first point of entry. We can keep some of the things inside context and throughout the life cycle, starting from our validation logic, our handler, our service, and our repository. Throughout all these components, we can share some amount of data so that we don't have to pass that data manually to each component. We can store that in context and we can take them out and share with other components. Then it also takes a connection, which is of database driver connection, pgx.connection. Then another struct called trace query start data, which will have an SQL string and all the arguments, all the parameters that we are passing to our SQL query. Then it will return a context by adding all this information inside the context. Then we are looping through all the tracers, the development tracer and the production tracer. We are typecasting into this interface, and then finally we are returning the new context. Same way, we are doing the same steps for the trace query end part. Now finally we'll write the function which is actually going to create our database connection, and it will have our loggers and tracers integrated inside it. We are going to call the function as new, and it is going to take a couple of parameters. First one is our config, the main config, the parent of all configs. Then an instance of Zerolog logger, then an instance of new Relic logger. We have two types of logger service. One is our application logger. The second one is the new Relic logger. Since to avoid name clashes, we will just import it by naming it as a logger config. And the name is, of course, boilerplate. Go boilerplate, right? I'll just run go mod tidy once so that we can get rid of any errors related to packages and fetching them. We are getting an error here because we have a clash for v4 of pgx and v5. Let's just delete the v4. Then we need another import for pgx0, which is basically an integration between pgx, our database driver, and Zerolog. This integration, which is nrpgx5, this is an integration between pgx, our database driver, and new Relic. And this is for our production setup. And for our development setup, we have this pgx0, which is an integration between Zerolog and our database driver. We'll have to give it a custom name so that they don't clash. And let me just run go mod tidy once so that it fetches that package also. And the error is gone. Okay, now let's see what's exactly happening inside this function. How are we creating a new database, which is of type struct with two fields. One is a database pool, the actual pool of connections. And the second one is the logger for logging different operations in our database connections. At the start, we are taking the host from our configuration and the port. We are converting the port from a number into a string, and we are passing both of these into this function, which is join host port, which basically combines the host and port so that we have a structure like this, which we can reuse again. Now here we have our host and port. Next, we are taking our password and we are escaping all the URL encoded stuff. If you don't do it, you might face some issues because you actually have to URL encode your password before you can use it. Then finally, we are building a string. Whenever you see fmt.sprintf, which basically means that we want to format a particular string and we want to return that and store it in another string. So this particular method can format a string and returns a new string. And all these %s are basically placeholders, and you have to provide the values in the same order as you are writing this %s. So the first one, this is the Postgres scheme to connect to the Postgres database. First, we are passing the username. Second, the encoded password, the URL encoded password. Then at host and port, this will have your host name and port joined using a colon, then the name of your database, then whether SSL is enabled or not. For local connection, the SSL will be disabled. For production, the SSL will be enabled. Then finally, we have a URL of this structure with all the appropriate values: our username, password, host, port, the name of our database, and then we pass that particular string inside this function, which is parse config, which basically builds a config which is suitable for our database driver and returns it into this pgx pool config. Since we don't want to create a normal database connection, we want to create a pool of connections. That's why we have to pass this DSN inside this function so that we can create a pool. If there are any errors, we return here and don't proceed. If not, then we proceed. At this point, we are saying that if we have a New Relic application already, then for the tracer part of our pgx pool config in our database driver, it natively supports integrating other tracer, whether it is development tracer or production tracer like New Relic or OpenTelemetry. We can create a new tracer and pass it inside our database driver, and it will handle instrumenting different parts, different components inside the database driver. So if the New Relic application exists here, it means that we have enabled it in our environment variable and it can add a tracer there. Then, as I said, we have different configs for development and production. So if we are in local, what we are doing, we are getting the log level, whether it is debug. Usually for local, it is debug. Then we are creating a new pgx logger, which we created a function in our logger.go file, and we get that instance of pgx logger here. Then what we are doing, if New Relic configuration is enabled for this environment, we are passing two different type of tracers inside this. One, which is the New Relic tracer, which we inserted here, that we are reading the value and passing at the same time. The second one is the local tracer, and the priority of New Relic will be more than the local tracer. That is assuming the New Relic configuration is enabled for this environment. If not, we are just building a local tracer and passing it as a value for the pool configs tracer. And after all this done, at this point, we are creating a new config with a new context. We are not taking or deriving from an existing context. We are creating a new context. When you say context.background, which means you are creating a new context, you're passing the config that we have built so far. And finally, we get a pool. If there are any errors creating this pool, we return from this point. Otherwise, finally, we create our database struct. In the pool field, we pass the created pool, and in the log field, we pass the logger. Now that finally we have a database pool, we want to check whether we are able to connect to our database or not. And we do that using the ping function. The whole purpose of this ping function is basically acquiring a new connection and keeping it inside the pool, and also running an empty SQL statement just to verify that everything is working fine or not. Since in a pool based setup, we are creating a lot of connections and keeping them in hand. That's what ping does. It creates a new connection and inserts it inside the pool. And we are creating a new context with a timeout of 10 seconds. Here we created a variable. Here we should take this variable to the top. Let's say we keep it here. We created a variable of database ping timeout of 10 seconds, which this basically says that if for 10 seconds we are not able to connect to our database, then we will error out and we'll return an error that failed to ping database. If not, we are successfully connected to database, and we finally return the database struct that we created here, which contains a pool of connections and a logger. And finally, we also need a method so that we can close the database connections. Since we have a pool of all database connections, if we abruptly end this process, then there might be some memory leak and there might be some corruption. That's why we need a proper method, a proper function to gracefully shut down all the database connection. That's why we create another function called close, which just logs a new message closing database connection pool. then it calls the close function, which is provided by pgexpool, and then it returns nil. And that's how we connect to our database with all our logging, tracing, monitoring configured. We also need a second file, which is called a migrator. I'll explain what this does. Migrator.go. This is going to be the content of this migrator.go. I have already explained that we have installed this command line tool, which is called Tern, from the creator of PGX only. This is a CLI tool which will take whatever. We should also create a folder here for keeping all our database migrations. We have this. Whatever SQL files that we add in this folder inside migrations, let's say we run a command. We have already added a task command for creating a new migration. So let's say we run a command called migrations.new. Now it shows an error that we also have to pass a name. Inside name, we say, let's say setup. And when we run this, it created a file called setup. And this is the structure we have to follow when writing migrations. This comment has to be here because whatever we write on top of this will be the up migration, and whatever we write below this, it will be the down migration. When we are talking about database migrations, we have two types. One is up, one is down. We use up migration when we want to go ahead of our schema, when we want to create new changes. And down migrations are basically for rollback purpose. Let's say you messed up some migration and something broke in your production. Then you want to go to the previous version of your database. That's where rollback comes in handy. But in my experience in the last few years, the down migration, the trend of down migration has significantly come down. These days, people only do up migrations. So if you need some change, which makes you think that you should go one level back, one schema back of your database, then you should consider that as an up migration and create another file and apply on top of that. Instead of going one step back, you just add that as a new change on top of your database. So we will not be writing down migration. We'll just write up migrations. So we won't have to worry about this. Now, coming back, we have a CLI tool, which is Tern. When we run migrations up, it takes all the SQL files from this folder, migrations folder, and it applies that migration on our database. But when we are deploying to production, we want to have a setup that after deployment, when our app is starting up, we want to auto apply all the migrations instead of creating an SSH connection to our server and manually installing Tern, the CLI tool, and applying migrations there. We want to just apply the migration through our code when our application starts. And that is the purpose of this file, which is the migrator.go. It has one function. I'll explain what it does. First, we are embedding all the migrations. So this syntax, when we say go :embed and the path of the folder and all the files that it should include, define this variable as of type embed.filesystem. This whole thing, what it does is it takes all the files inside this migrations, all the SQL files. And when we build our project, when you run go build, it gives you a binary depending on what operating system that you are running on. In Mac, on Linux and Windows, it gives you exe, etc. It gives you a binary. And when you use embed, all the files, all the SQL files inside migrations will be embedded, will be saved inside that binary so that we can use it later when we are applying the migrations in our production. And that's the use of this. Now we have a function called migrate. It takes 3 parameters. One is a context, so that if we want, we can return early and things like that. Then a logger and our main config. And it returns an optional error. If we face any error, it returns an error. Otherwise, we return nil. Same way, the connection step that we are doing in the database.go file, we do the same thing here also. We create a DSN. DSN is basically the URL of the final database connection that we use to connect to the database. But now at this step, we don't really create a pool. Since this is a one-time execution, we don't really need to hold different connections for applying migrations. When our application starts up, we create a new connection to our database, apply the migrations, and close that connection. That's a one-time thing every time you deploy your app. That's why we are not creating a pool. We are just creating a new connection, and when this function returns, we are closing that connection. That's why you use defer. Then we install this package called Tern, which is a package which gives you programmatic access to all the functionalities of the Tern CLI tool. You can do all those things in code also. Then we just create a new migrator. We mention what is the field in our database which contains your schema version. Then we read all the files inside our migrations using the file system standard library package. We all load the migrations, get the current version, and then we finally migrate. Every time we apply a new migration, the database, it has a table called schema version where it tracks what is the latest version of the migration that we have applied. So at this step, what we are just checking if the schema version has incremented or not. If it has not incremented, which means that there are no new migrations to apply. If it has, we say that our migrations has incremented from version 2 to version 3. And this is the reason every time you deploy, you should try to create a new migration file, even though it sounds obvious. Sometimes what we do, we just edit the existing migration file. If you do that, that migration will not be applied because the CLI tool, Tern, whatever we are using, it records what is the latest version of the migration, and it will not scan the new changes in an existing file. It will only look for new files in your migrations folder. So always try to create new migrations every time you are thinking of applying a new change on our database. With that, all the database related logic is done. Then we can move on to other modules. Before you continue, let me tell you a little bit about the sponsor of this video. Sevala basically is a platform as a service provider. If you have used platforms like Vercel and Netlify, Heroku before, then this is a very good alternative to that. All these other platforms, all the platform as a service providers, they charge you and your team per seat. But Sevala is one of the only platforms which does not have a seat-based pricing. So you are going to get a very good cost-effective bill. You can host anything on Sevala, whether it is your application, your databases, your object storage. One particular feature that I personally use is the native Postgres extension. So if you are building with AI applications, you are building things like RAG applications or recommendation engines or semantic search, you get native vector operations with similarity search functions. Also with extensions like PostGIS integration, you can handle spatial data for location aware AI applications. The managed databases, they handle backups, auto scaling based on CPU, RAM, and storage, all independently as your datasets grow. On top of that, Sevala runs on Google Kubernetes engine with around 25 data centers globally. And it also makes use of Cloudflare Edge Network with 260 plus points of presence around the world. So you get native edge speed in all your applications. It also handles horizontal auto scaling automatically. If you are building something like compute intensive model inference, it scales with demand without manual intervention. And no per seat pricing also means that your entire machine learning team can collaborate freely. And that kind of pricing based on compute is perfect for AI workloads. And since Sevala uses Cloudflare R2 behind the scenes for their object storage service, you get zero egress, which is ideal for large model files, your machine learning model files, or your training datasets. So if that sounds interesting to you, then you can click on the link that you can find on the top of the video or in the description of the video, and you can claim $50 worth of credits so that you can try out all the services and see for yourself if it suits you and your team. Next up, let's move on to our errors package. Inside this, we'll keep all our utility functions, all our variables, so that we can create and send errors instantly from anywhere in our application instead of doing all the boilerplate thing again and again. We'll create a file called http. And we'll create another file for creating the types of errors. And this is going to go in our http.go file. So the whole point of this file is we want to create a custom error type instead of whatever error type is provided to us by libraries like PGX or Echo. We want to create our own custom error type solely for the purpose of sending to our client. Now the client can be a Postman or Insomnia client or a front-end web application. Or later on when we integrate our OpenAPI contracts, it can be our OpenAPI testing interface, whatever client that we're using to test our APIs. So that the client gets a meaningful and a clear message and actionable steps they can use to fix their errors, or if the error is from our side, then they'll know that information. So there are a couple of types that we are creating here. Let's go through them one by one. This one, field error. This is a struct, and we are creating this so that if we have any form interface in our client and the user has typed something, let's say we have a form where we are taking name, email, password, address, and all the information about the user. So when that form is actually gets submitted and an API call gets made, we'll obviously validate that. We have not gotten to the validation part yet, but we will validate that particular payload. And after validation, we will, if all the data is correct, all the data is exactly in the format that we are expecting, then we'll let the request go through and the handler will process it and forward to service and repository, etc. But if there are some errors, let's say the name, the minimum number of characters for a name should be 3 characters, but the user has sent 2 characters. Then we want to send a message to the user that for this particular field, so inside field, we'll keep the value as name for the field name. This is the error. And in the error, we'll write whatever meaningful message that the length is too short, the minimum number of characters should be more than 3, whatever message you want to send. The field error basically deals with all our form-based errors. And this is usually an array. Here you can send, this is the final error struct which we are sending. And inside this, we have a field called errors. And inside this, we have a slice of field error. So if we have errors from multiple fields, we can send all those errors at one go. Next up, we have an action type. This is useful in scenarios where, let's say, the user session is expired. And for that, we have sent an error code of 401. But we also have sent an action, this action, which is another struct, and this has a type, a message, and a value. If a user session is expired, we want to send a 401 unauthorized error. And for that, in some cases, in some particular cases, we also want the user to get redirected to another route. And we want to send that piece of information through our error struct. That's why we have kept action related information in this. So this is a pointer to a struct, which basically means that for most of the errors, we are not going to use the action field. We'll mostly use the first 4 fields. Again, this is also a slice. And since the 0 value of a slice is nil, this also will go as nil if there are no errors. So the first 4 are going to be present in all our errors. Now, the first one is code. Code is basically some kind of uppercase code. For example, let's say we are building a to-do application, and inside that the user has requested for a to-do with an ID which does not really exist. So we want to send an error which looks like to-do not found. We want to send a string in this format with uppercase snake case format, so that in front end we can have a logic where the front end will go through these codes, and depending on this code, the front end can show a more user-friendly message, a more personalized message. That's the whole idea of sending a code. Otherwise, the front end has to show the message, and usually the message that we send from backend, sometimes it is user-friendly. That's our idea, but sometimes we want to keep it short and let the front end and let the client handle it, especially if it's a front end back end kind of setup. For that, we use the code field so that the front end can parse through it, and depending on that, it can show a personalized message. For message, we are sending whatever the description of the error message is. to do not found, not ever in a readable format instead of a uppercase snake case format. Then we have the status. This will be the HTTP response status code, whatever 400, 200, 201, etc. Then we have another field called override. This override field is not used all the time, but we have added this so that for some cases, let's say we have a email OTP based authentication process in our front end. And for that particular workflow, we are limiting how many times a user can type a wrong OTP. So let's say we have kept that limit as 4. You can only type the wrong OTP 4 times. After that, your account will be blocked for the next 24 hours. Now, the first time the user types a wrong OTP, we want to send an error, of course. The error will be something like 403 forbidden. Right? And with that error, we want to send a message that you have typed a wrong OTP once, you have 3 more attempts. Right? It is a message that is coming directly from the backend. And only we have that data that the user has 3 more attempts remaining. The front end does not know it. So for these kinds of cases, what we want to do, we want to override the message, the user-friendly message that the front end is trying to show. We want to override that. We are saying that we are already sending a user-friendly message, so you don't need to parse the code and show another message. We can directly show whatever message that is coming from the backend. So for this kind of collaborative workflow between the front end and the backend, we have kept a field called override. Next, we are creating a receiver method called error on our HTTP error. And this is how we can convert a particular type, whether it is a struct, whether it is any other type, we can convert a particular type into an error type if we add a error receiver with exactly this structure. And whatever string that we want to return, that is up to us. We can, let's say, we can merge e.message with, say, e.code. Right? We can also do this, but we have to return some kind of string. That will be the error the Go process will detect. Then we are also defining a receiver method called is. This is for comparison purpose. We'll see how it works later on. And these are some utility functions. Now, moving on, let's define what are the different types of error. Now, there are a lot of different types of error codes in a typical backend, but there are a few codes which get used a lot, around, let's say, 95% of the time. And for that, we want to create a few utility functions so that we don't have to write the whole thing again and again. We can just call these functions and pass around some defaults, and that will create a full instance of our HTTP error. For that, I have created a few types, pasted here. These are all the types that we need. If you are already familiar with some of the basics of response codes in a HTTP backend, then this will be very familiar to you. First one is a new unauthorized error. This is a function which takes a message and a value for overriding, whether you want to override or not. And then it returns an instance, a pointer of HTTP error. In code, we are basically taking the HTTP status unauthorized, which is 401, and we are fetching the status text for that. So for 401, what we'll get is unauthorized. We'll get something like this, unauthorized. First one, this gives us the number 401. And when we pass 401 into this function HTTP status text, this gives us this string unauthorized. Then we are using our utility function that we just created here so that we can convert it to uppercase with snake case. So this will get converted into this, and that will be the final value that we want to send in our code. In the message, we are passing whatever message that we got, whoever called this function. Then in the status, again, we are passing 401, the status unauthorized, who has a very readable list of these status codes. We don't actually have to write 401. We can just use the readable text. And then we pass whatever override value we have got from the caller of the function. Same way, we are defining a utility function for forbidden error, which is basically 403, and a bad request error, which is 400, and a not found error for 404, And finally, an internal server error, which is basically all the errors that is caused from our side, and that is of 500. And we have another utility function for returning a new bad request error. Especially, we use this for validation related purpose. And we use this one, the new bad request error, this one, for all the other purposes. And that's about all the custom error types that we are going to use in our application. Next up, inside lib, we want to create a folder called utils, and inside that another file named utils.go. And here we want to keep some of the utility functions that we'll be using, which does not really belong to any other module. That's why we are keeping it inside the lib folder. And for now, I just have one function that I frequently use, which basically takes any interface. So it can be a struct, it can be a map or any other type or a slice. Then it just marshals it into a JSON and it just prints it with proper indentations and etc. So if you just want to take a quick look at what are the contents of a struct, what are the contents of a map, and what are the contents of a slice, then we can use this function so that we can instantly take a look instead of debugging manually. And since we are already working in lib directory, let's jump into our module for handling background tasks. Now we need background tasks for things like sending a notification, sending an email, since these are asynchronous operations. And so instead of blocking a particular request, we can just delegate that to a background job handler, that we can instantly process a particular request, return the response, and on the background, we can start another process, another task, which will actually send the email. So we can definitely do that with a Go routine. We can process the request, send a response, and spin up a Go routine before we return that response. That will work, and that might even be a good solution for a lot of cases. But since as we are going with a production-based setup, I wanted to make this a little more robust. So we will be using a library called Asynq. This is a library which uses Redis behind the scenes to process background jobs, to execute them, to resend, to re-execute with exponential backoff, and a lot of features. It offers a lot of features, but we'll just keep it simple and initialize a server and use that server to perform whatever background jobs we have. For now, we will just keep it for sending our emails. Let's create a new folder inside lib called job. And inside this, we will have a file called job. This file will contain the service provided and managed mostly by the library Asynq. So the first thing that we need is define a struct which will contain the instance of the library. So let's run go-mod id once. So there's our gone when we install the library. Okay. Next up, we need a function which will actually create the instance of the library, and it will return an instance of the job service, which will contain client, the Asynq client, the Asynq server, and a logger for logging any critical details and informations. So for defining the function, this is what it is going to look like. We take a logger. We are basically following, I have not mentioned this particular term so far, but we are following this pattern called dependency injection. And dependency injection basically means instead of importing global variables, for example, if you wanted, we could have declared a variable called logger inside our file, which is logger.go here. And we could have imported that file everywhere, for example, here. But instead of doing that, we want to take the logger as a dependency through our parameter, through our function parameter. And that's how we want to use it. And one benefit of that is when we want to test our application, different modules, either unit test or integration test, since we are not using any global variables, we can specifically control what kind of logger that we use in our test environments. So if you want, we can create a different instance of the logger, which is specific for our test environment, and we can pass that. So that is one advantage of dependency injection. Second is it makes your application more explicit and less buggy. It's a good pattern, and we'll try to follow it as much as we can. Second, it also takes an instance of the config so that we have access to all the variables. For example, our Redis address, the URL where our Redis instance is running on, and we return an instance of the job service. First up, we take the address of our Redis URL and we save it in a variable. Then we initialize a new client, an Asynq client, which is coming from this library, by passing the address of our Redis instance. That's all it takes. Second, we also have to create a server. So the client is the one using which we will insert tasks, insert background jobs, but the server is the module which is actually going to execute those jobs. So for our server also, we'll pass Redis address and some config. For example, we want to keep the concurrency parameter as 10. So at a time, 10 concurrent jobs can run at the same time. And we are defining 3 different types of queues. One is for low, one is for default, one is for critical. So if we have different types of jobs, let's say for one, we have our email job, a job which sends email to a particular address. Then let's say we have other jobs. For example, we have a job which triggers when a user wants to delete their account. So if a user wants to delete their account, we don't really just take that particular request payload and instantly delete all the user data. That might work if your app is small and you're working in a development environment, but in production environments, if you have noticed this before, what usually happens is in any SaaS, whatever service that you're using, most of them follow this pattern that if you want to delete your account, you just register a request and you will be logged out, and it takes some time to actually delete all your data and actually delete your account permanently. And that happens through a background job. So for that kind of task, for that kind of jobs, we will use the priority as critical. But something like email, we can keep the priority as default or low depending on our use cases and how critical is sending the email. And at last, we pass all these initiated configs and the client and the server and the logger and return a new job service. Then we need 2 different functions. First, to start our server, and second, to stop our server. Again, as I have mentioned before, throughout our application, we'll have different modules. We have database, we have Redis, we have this background job processing, and all of these services, they need to be properly shut down. Instead of abruptly shutting down all our services, we'll follow good patterns. We'll follow the actual recommended way to shut down these services. So we'll create 2 functions, one for starting the server, which will basically create a new serve mux, and it will register a handler. We have not created the handler yet. We'll create that soon. Then we log a message that we are starting our server, and here we start our server. Similarly, for stop, we just call this function called shutdown. We log some message and we close the client. So let's go ahead and create these handlers and these task types. So for a task, let's create a new file called email, and here also the package will be job, and we are creating a variable called task welcome, and it is a job of type email and the key is welcome. And the payload we are going to pass is 2. Inside this, we'll send the email address where we want to send the email, and then the first name in case we want to add the first name to customize the email a little more. Then we declare a function called new welcome email task, which takes the email address that we want to send to, the first name that we want to customize with, and it returns a new instance of asynq task. This comes from the library asynq, or an optional error. One thing to keep in mind is error always comes in the second position. Wherever we have this pattern where we, in the first position, we return the data, in the second position, we return the error, either an actual error or nil if there are no errors. The first, we want to convert whatever payload we have received. We convert it into JSON. First, we load it into a struct, which is the welcome email payload, and then we marshal it into a JSON string. That's the input type we need for creating a new task. And at last, we create a new task, which is of type task welcome. So instead of using hard-coded strings, we have created a new variable so that it's easy to read and it's easy to maintain. The task is task welcome, and this is the payload, which is the stringified JSON. It's basically in Go, it's a JSON byte. And these are some configs. The maximum amount of times we want to retry this task. In case it fails is 3. We'll try 3 times and then we'll stop trying. And the queue it will go is default. Since it's not a very critical task, we are putting it in the default queue so that if there are tasks which are in critical queue, they will be executed first. And the timeout of this task is 30 seconds. That's the email task type when we want to send a welcome email to a user. And then at last we want to create the handler which will actually process the task. So for this, let's create handlers, and this will be the content. We have not created this email module yet, so let's get to that first and come back to this file once that is ready. So inside lib, let's create a new folder called email, and inside this again a client.go. Now this file will contain the actual logic which will send the email. Now the background job that we created, its task is to trigger the function which will send the email. It cannot actually send the email. It's just a background job processor. It can run all types of tasks. But to actually send the email, we need an email client, an email service. So for that, we will be using Resend. I've mentioned this at the start of this video. Resend is a modern email provider. You can register here, get your key, and put it in the environment variable. I'll show you what the structure of the environment variable looks like. But after that, you can use the service. I'll not be going through how actually you can do all those steps. You can just follow the docs. They have very comprehensive docs. You can go to the section on Go and you can follow the patterns here. Right now, going back, let's first declare a new client for sending our email. For this, we'll need to use the version 2, and let's just run go mod tidy so that this library is installed. Next, we need a function, an initializer function, so that we can return an instance of this client struct. That, let's declare a function, which is new client, and it will take our config instance, and it will take our logger, and it will return an instance of this client. And we'll just use this syntax to initialize and return a new struct. In the client section, we are using resend SDK with the new client function and passing our API key and the logger. I actually forgot to add the integration in our configuration. So let's go back, config. We'll have to create a new struct here. So let's create a new struct here, which is called integration config. Inside this, we'll keep the recent API key, and this is what the environment variable is going to look like. And we'll pass it here, integration config. Now going back, there is no error. We have this config here, and we are returning a new client. Next, we need a function which is actually going to use this recent SDK, this initialized SDK, this initialized client of recent, and it is going to send the email. So we'll need a couple of stuff here. The email address that we want to send to, the subject of the email, the name of the template, we will create this variable after this, and the data. And data will basically keep some of the parameters like what is the redirect URL, what is some kind of data that we want to show, whatever, any kind of template params that we want to keep or send in the email, we'll just pass it here, and it can return an optional error. So in the first line, what it's actually doing is it's reading all the emails from this particular path, is templates/emails, but we don't have a templates directory yet. So what we will do, let's just go ahead and create a new folder inside backend called templates, and inside that another folder called emails, and inside that we will store all our emails. We have not gotten to how we can actually create and format and store the email. We'll be using React email for the whole workflow. I'll show how that works, but for now, let's just create the folder and keep that empty and finish this integration module first. We'll declare the template variable. So for that, let's just inside the email folder, let's create a new file and we'll name it templates.go. So as we create more and more email types, we'll add more templates here, but we're creating custom type of type string, but we are naming it template so that it's type safe and it's easier to understand what type we are referring to. Going back, we don't have any error now. We already have this template variable declared in this file, And since the package of both these files, here the package is email and here also the package is email, and that's why we can access the variable that is declared in a different file in this file, in case you are confused about that. Okay, next up, we are reading this particular path, which is templates/emails and the template name. Whoever calls this function, it will pass the name of the template. For example, it will pass this one, right? Template welcome. Then we are using this package called HTML template. Now it provides some useful functionalities so that we can parse HTML and we can pass some data in the placeholders. I'll show how the whole workflow works once we generate our template. But for now, let's continue with the integration. If there was some error while parsing this template, we'll send a meaningful message and return here. Then we are creating a new buffer and we are actually executing this template with whatever data is passed. So we have an HTML file and it has some placeholders, and whatever data that gets passed inside this function, we want to inject that data inside the HTML. That's why we are doing this step, which is template.execute. If we get some error while doing this, we are returning another error and we are stopping the execution of this function here. And finally, we are creating a format of recent.send email request. Here we'll be passing from, and here let's the line boilerplate. It will be in this format, which is basically boilerplate, and inside the Angular braces, this will be the email onboarding.recent.dev. So while you are in the development environment, when you're using recent, you can use this particular email to test out how your email delivers, how it looks like, and all the workflows. When you go to production, you can go to your recent dashboard and you can configure your custom email, whatever domain you have. Inside too, we are passing a slice of strings for all the addresses that you want to send this email to. In the subject, whatever subject that is passed to this function. And finally, inside HTML, we are passing this body, the body where we injected all our data and we created the final HTML. And finally, we are sending the email, and if we face some error, we return here. Otherwise, we return nil. This is the whole send email function that actually sends our email using the recent Go SDK. Now, another thing that we need for testing purposes is a preview data. So let's create a file called preview.go, and inside that we'll keep a map. So for welcome email, we are using this preview data, which is user first name, and the value is John. And finally, we want to create a utility function to send different kinds of emails. Instead of using the send email function in all places, we'll just create one utility function so that it's easier to call, and we can keep the scope limited to this package. So the file name will be emails.go, and inside this we'll create a function called send welcome email, which will take the email address that we want to send to, the first name of the user, and it constructs a map using the variable name user first name and passes whatever first name that it has received, and it triggers this particular function, which is send email, and we pass the to email address, the subject, which is welcome to Boilerplate, and template welcome, which is this variable, and the value is welcome here, and whatever data that we receive, which is this part, so that it can be injected, which we saw in this function at this step. This is the complete implementation of our email sending logic. Now we can go back to our handlers. The error is gone now since we have created our email sending logic. Now that we have our email client declared, we can go ahead and implement our final background job processing handler. We create a variable called email client, and we'll initialize the email client and assign the value to this particular variable. We have a function called init handlers, which will initialize all the handlers and assign the value of the client to this particular variable. It is a receiver, so that we can directly call it on the job service. Then finally, we have the task, which we used here, handle welcome email task. When the task type is this, is task welcome. If you click on this, which is the email welcome. When this particular task is triggered, this handler will be executed. So now this takes two parameters. One is a context so that the caller can pass any additional data, or it can control whether the execution should continue or should drop, etc. And a async task instance and returns an optional error. So first we create a new payload, which is of welcome email payload, which has a two email address and a first name. Then we take the payload which is assigned to this particular task, which is saved inside this particular task, which we can get using t.payload, and we unmarshal that. So this has a marshal JSON, a stringified JSON, and we load that inside this particular struct. We take the data from the JSON and we load it inside this particular struct. And the reason we stringified the JSON, we converted into bytes, is we send the data, we send the payload from the client to server. It has to be serialized. And when the server finally receives the data, it will deserialize into this particular struct. Before it can read the value, it can pass the value to the appropriate parameters. Then we log the event so that we can later see and debug whether the email actually went through or not. And finally, we call this particular function, which is send welcome email. We pass the two email address and the first name. If there was some error, we log the error and return it. If it was successful, then we say email sent successful and we return nil. And with that, we have our background job processing module ready for sending emails. Later on, if we have more kinds of jobs that we want to add, then it's a pretty simple workflow. We just come here, instead of email tasks, we create a new file. Let's say we have tasks related to user, for example, deleting users data. So we create another file called user tasks, and there we declare a variable user : delete. And we come here, we create a new handler, which will actually execute that particular task by calling whatever database function we need to call, etc. But our framework is ready and we can expand on it, but we don't have to change the core of the framework. We just, every time we need a new kind of task, we just add a new handler, add a new variable for the task, and we just connect them. And that's the beauty of having a boilerplate which has all the patterns figured out, so that you can move fast, you can focus completely on your business logic, and you just keep adding stuff on top of your structured framework instead of reinventing the whole wheel every time you have a new feature. Next up, we can go ahead and let's create our server. We have pretty much all the dependencies ready. So we can go inside this and create a new file called server.go. Now this file will contain the core struct, the core data structure, which will contain our config, the logger, our new Relic logger service, our database instance, our Redis instance, our HTTP server, and our background job processing server. Right? We'll take all these different instances of different servers, different services and modules, and we'll put all of them inside a single data structure. And we call that as a server. And using that server, by passing an instance, a pointer to that server, we can establish this dependency injection workflow. So that will pass the pointers everywhere we need one of these things. For example, if we need database, we'll pass the server a struct, and we can take out the database instance using that server instance. So let's create that struct first. So we'll create a struct called server, and it will have all these things: config, our logger, our new Relic logger service, our database instance, Redis instance, HTTP server, and our background job processing server. Great. Now that we have added all the appropriate inputs, there are no errors. Now we can go ahead and implement a function which is going to initialize all these different servers and services, and it is going to put all of them, the initialized versions, inside this struct, an initialized struct of this server struct. And this is going to be our initializer function. So there is an import error here for this particular package called nr redis. We actually need the version 9 of this, and let's go ahead and run go mod tidy so that this error is gone. Great, the error is gone. Let's see what we are actually doing in this function. We are taking a couple of things. One, an instance of the config, an instance of the logger, an instance of the observability service, which is the new Relic service. Then we are returning an instance of this server. So you'll notice this pattern called new in pretty much all the packages. We create a struct, and below it we create a function named new, which takes a couple of things to initialize the struct and returns a pointer to that struct, right? So when you go through this boilerplate yourself, I'll upload all this code to a GitHub repository. When you go through the code yourself, you'll see the same patterns repeating everywhere. And it's not a coincidence. I've tried to keep that part consistent so that the more you work with the code base, the more you work with this boilerplate code base, the more you're familiar with this pattern of this whole dependency injection, declaring a struct, using an initializer function like new, and returning an instance of that struct. All these patterns, they get repeated in every single package. Over time, it will become your second nature. So if you're confused now, then no need to worry. The more projects that we build, the more familiar you'll get with these patterns. First, what we are doing, we are creating a new database instance. So we have a function called new inside our database. If you go inside this, we have this. We created it a while ago, and this function is ready for creating an instance of our database. And we call it. If there are any errors, we stop here and return. Next, we use this package called go Redis for connecting to a Redis instance. And we create a new client by passing the address, and now we have a Redis client. Next is, at this step, what we are doing, if we have our observability service enabled, if we have our new Relic integration enabled, we are checking if it's already initialized. And if it is initialized, then it will not be null and will come inside. And what we are doing, we are adding a hook. So hook is basically, we can pass this logger, this tracer, basically the observability tracer, inside our Redis client, so that whatever critical events happen, whatever debugging logic that gets executed, that will be processed through this logger, through our new Relic logger, so that we can get all these logs inside our new Relic dashboard. So that's the whole idea. And this package, this particular NR New Relic Redis package, it comes from New Relic only. They have very good integrations with all this ecosystem of a Go backend. That's what we are doing at this step. Then, as we did with our database, we are trying to connect to our Redis instance. If it's not successful, we are still going through, because initializing Redis is not very critical, especially for our backend. So we are not panicking here. We are just passing through, and we'll see an error getting logged, and we can debug from that log. Then we are creating our new background job processing service, and we are initializing all our handlers, and we are starting our background job server. And finally, we are creating our server struct by passing all these things that we just initialized, and we are returning a pointer to it. As I said, the patterns will keep repeating. So now that we have a service, we have a struct, we have an initializer for that struct, for that service. Now we need some way to start that service and to shut down that service, so that we have a very clean, graceful shutdown workflow. For that, we'll need a couple of functions. First is set up HTTP server. Now, if you notice, inside our struct, we have a field called HTTP server. But in this function, we have not initialized it. And for that, we have created a new function, which basically takes an HTTP handler and initializes a new HTTP server by using different configs. First, it takes port, our handler that we passed here, and different timeout values. It creates an instance of HTTP server, and it assigns that into this server struct inside this field. That's what we are doing here. These two functions are pretty self-explanatory. And if at this point the server is not initialized, we throw an error, then we log that we are starting our server, and this function, finally listen and serve, this starts our backend server in this particular port, whatever port that we have configured, which can be 8080 or 3001, whatever you have configured in your environment variable. And finally, we create a function for shutting down our server gracefully. So we do that using HTTP server's shutdown method. And in the same method also, we close our database connections, and we also stop our background job processing server. And finally, we return nil if there are no errors. And that is our whole setup for initializing and running our server, the actual HTTP server, which is going to take requests and do all different kinds of processing, etc. Now that we have our server ready, let's go ahead and implement all our middlewares. The most important middleware that we are going to use repeatedly is obviously the authentication middleware. So let's just create that first, auth.go, and this again will have a struct which is going to be called auth middleware, and it will also have an initializer function. We have created a struct. Inside that we have embedded our server so that we have access to our config, we have access to our logger, and whatever we need using this server instance that we are passing as a dependency into the initializer function, and returns an instance of auth middleware. Next, we just need one function using which we can check whether the request that is coming, it is authenticated or not, which basically means it has all the session tokens, GWT tokens, whatever we need. And if it not, then we send an appropriate 401 unauthorized error. So we are actually going to use the Clerk SDK for this. So let's just first fix the imports. This is going to be v4. So let me just run go mod tidy, and that will fix all the import errors. Apart from that, there is one more error here for getting the request ID. Now we'll have to create this function get request ID. So for that, we need to create another file called request id.go. I'll explain why do we actually need a request ID in the first place, but let's just see how we are implementing it. By declaring two variables, one for the name of the header where we are going to find or store request IDs, and the key of the request ID, which is just request ID. And this is going to be a middleware. Will initialize all the middlewares in our final router, but this we are declaring as a middleware. This function is actually returning a new middleware. So in the return type, you can see this returns a echo.middleware func. So inside this, we can declare a handler which has access to the context. Now every time a new request comes to our server, a new context gets created through our web framework, which is Echo, and we can access that. And using that context, we can get access to different information about our request. For example, the path parameters, the query parameters, the payloads, and everything related to our request. Now, at this step, what we are doing, we are trying to fetch the request ID using this particular request ID. And the reason we are doing it is because the whole concept of request ID comes from the practices of observability. And since we don't have a complex system integration here with multiple servers and load balancers, etc., when people actually deploy their servers, let's say in Kubernetes and other cloud infrastructure, they have things like load balancers and Kubernetes pods, auto scaling, and everything configured. And in that kind of setup, the first point of contact is going to be your load balancer. Whatever request comes from the internet, that is going to reach your load balancer first, and that load balancer is going to forward that request to your backend service. And that's what we are trying to do here. If our request reached the load balancer first and that load balancer created a new request ID, then we are trying to fetch that request ID, because the whole point of tracing and observability is every time a new request starts, that request will be given a particular ID, a unique ID, and all the components, all the services that it touches will have the complete transaction in our dashboard, so that we can take a look at the whole workflow, where it started, where the request reached, what are the logs that was caused by a particular request. So using the request ID, we can connect all these different interactions into a single transaction. And since we don't have a load balancer kind of setup, what we are doing, if the request ID is an empty string, we are creating a new ID using this UUID format. If you're not familiar with UUIDs, this is what it looks like. If we paste here, this is what a UUID format looks like. This is fairly unique, and it's a very good candidate for using in different identifiers, right? Once we have request ID created, we are setting it inside our context. We are saving it inside our context. So if you remember, a context, especially when we are talking about a web framework, it does not matter what framework you are using, whether it is standard library or something like Echo, something like Gin, Fiber, it does not matter. Every framework, every kind of setup offers this context feature, and you can use context as kind of a limited storage, a temporary storage for the whole life cycle of the request, from the first point of contact, which is going to be your routing layer, up to your repository layer, passing through your handler, services, and everything. That's the reason we are creating a new request ID and storing it inside our context. Then we are also setting header, the X request ID header with the newly generated request ID. After that, we are calling this next function. So in middlewares, we have this special function called next, which basically hands over the execution to the next middleware so that it can pass on to the final handler. So we are taking that context, the modified context, and we are passing it inside next, and we are handing over the execution to the next middleware. And we are also declaring a function. It is kind of a utility function which takes a context which is of type echo.context, and it takes out the request ID from the context and returns it. So instead of writing the whole thing again and again, we can use this utility functions to make our code a little shorter. Now, if we go back to our auth.go, we don't have that error anymore because we just created this function. And we also added the functionality to create a request. Okay, let's understand what's happening here inside our require auth middleware. Again, this is also a middleware itself, and we are using Echo's wrap middleware function so that we can add some of our custom logic. Then we are using this function provided by Clerk SDK itself, which is with header authorization, which basically checks if your token, whatever JWT token, session token, is present or not, and if it is valid or not. Otherwise, it sends an error, right? They provide this very handy function which we can use for checking authentication in our middleware layer. And inside that, we are also passing a custom error handler. So if you don't pass this, then what happens? They will just return an error with status code of 401 and message of unauthorized. But since we want to customize every single error message in our own style, in our own custom style, that's why what we are doing, we want to override the error handling logic, and we want to create an error format that matches our own custom error, and we want to send that. We are setting the content type application JSON. The status code is HTTP status unauthorized, which is basically 401. Then we are creating that JSON and sending it here. And if that was not successful, we are logging that error. Then we come inside our middleware logic. Since we used Echo's wrap middleware function, we can add some of our custom logic before the actual middleware runs. Here we are starting a timer so that we can measure the whole latency of how much time a particular request took. Then we are using this particular function which is provided by the Clerk SDK, which takes out different crucial information from the context. So when we execute this particular function, which is with header authorization, it authenticates a particular request using a token in the header or a token in the cookie. Then it embeds some of the crucial information, the authenticated information, inside the context. So we can take that context and we can extract some of the information from the context. And we save it inside claims. And inside claims, we'll find a couple of useful things. But before that, if fetching the claims was not successful, we log the error and we send an error called this request is not authorized, again, which is 401. If that is successful, then what we do, inside the claims, we'll get some useful information. For example, the ID of the user, the role of the user, and what are the different permissions of the user, if we have configured custom permissions for the user. And we add all this inside our context so that later on, inside our handler layer or service layer or our repository layer, if we need the user ID or the user's role, we can directly take it out from the context instead of us manually passing the user's ID, user's role one by one to explicit parameters. And finally, we log the request with different keys. The function name is require auth, the user's ID is this, the request ID is this, the duration is this, which is basically how much time it took to do this whole operation, and the message is user authenticated successfully. And if you notice, this part is important here in our whole logging, monitoring and observability setup. When the request ID in a log and in a particular trace are same in our dashboard, in our new Relic dashboard, but if you are using any open source solution like Grafana, you can correlate them using a particular request ID, and you can see all the related information in the same place. So if you click on a log, since it has the same request ID, you can see the whole trace of that log, whatever functions it touched for that request and all the information surrounding it. That's why it's important that we use this request ID key here and pass the appropriate request ID using this function. And that is our auth middleware. Next up, we need a middleware which is going to deal with our context. By deal with, I mean it is going to do some operations and it is going to save some things inside our context, which is going to come in handy later on, especially for the new Relic integration. So let's go ahead and create a new middleware called context dot, and I'll just paste the content here and we'll go through it one by one. We are creating 3 variables so that we don't have to hard code these strings. Then we are declaring a struct called context enhancer and we are initializing it below it. Next up, we have a middleware which is called enhance context. What it does, first it fetches the request ID from our context. The request ID middleware that we created here, it will create the request ID and save it inside the context, and here we are trying to fetch the request ID from the context. Then we are logging it here, right? Our first log. And what are we logging? We are logging our request ID. As I said, all the logs with the same request ID are going to get grouped, and it will help us later in our new Relic dashboard when we are trying to debug things, when we are trying to understand different interactions, different transactions in our app, right? We are adding a request ID, the request method, the path, and the IP address from where the request is coming from, right? Then what we're doing, we are starting a new Relic transaction. Now, transaction is a concept in New Relic, which is kind of like traces, where you create a transaction at your first point of contact, and from that point on, all the places, all the components, all the functions, you can take that particular transaction and you can keep adding more data to it to make it more useful, and the whole transaction will be visible in your dashboard, and you can see that your first point of contact was this middleware called enhance context, and then you touched your handler, then you touched your service, and then you touched your repository, and this error showed up in your handler layer, and this success message showed up in your service layer, etc., etc. And this is very convenient when you are actually trying to debug things in your production. This is what we are doing here. We are creating a new transaction and we are taking the trace ID and span ID, which is also some of the parameters which come in very handy when you are building traces. And these are provided by a new Relic integration. You don't have to create them manually. And we are adding those to our context logger. Then we are extracting the user ID. So from our authentication middleware, we'll get the user ID and we are saving it inside the context. So using this function called extract user ID, we are taking out the user ID and we are also adding it to the context or to the transaction. Next up, we are also adding the user role to the transaction. Then finally, we are setting the whole logger, the whole transaction logger inside our context, so that in the downstream layers, in our handler, in our repository, in our service layers, we can use the same loggers, the same instance of the logger. All the transactions are grouped and they are part of the same interaction. Then we are creating a new context and returning it to the next middleware. We also have a couple of utility functions here so that we don't have to write the repetitive code every time you want to get the logger out of middleware or get the user ID out of middleware. After context, let's go ahead and create our tracing middleware. Now, this is again another New Relic integration, which is going to help us with creating our traces and adding more data, adding more useful data to our traces or our New Relic transactions. So this is going to be the content. I'll have to run go mod tidy once so that this import errors are fixed. Now, again, we are creating a struct, adding two fields, one for our server so that we have access to different configs and different instances. Then this is our New Relic application. Then we are creating a new instance of our tracing middleware, which returns the initialize struct, a pointer to the initialize struct. It has a New Relic middleware receiver function, which is basically a middleware function. So if we have not initialized the observability config using New Relic, this is going to return a normal middleware. But if we have configured it in the upstream layers, then we are using this echo integration of New Relic, which is coming from this particular package. And we are wrapping our whole app using our New Relic integration. And because of this, we'll get access to a lot of nice features like logging and monitoring and metrics and all the different things. All of that is happening because of this line. We are wrapping our whole app using our New Relic integration. Then we also have a middleware, which is for enhancing our tracing data by adding some more useful data. So first thing we are doing, we are taking out the transaction that we have saved inside our context in upstream layers, in particularly this middleware where we saved our transaction inside our context. So in our tracing middleware, we are taking out the transaction and we are adding some more attributes. Attributes like our service name, which is going to be something like Go Boilerplate, and the environment that we are running in, either local or production, the IP address and the user agent from where the request is coming from, whether it is a browser or it is a client like Postman or it is a client like Swagger, etc. Then we are taking out the request ID from the context and also adding that to our transaction. Then we are taking out the user ID and adding that also to our transaction. After that, we are passing the execution to the next middleware. And if we face any issues while we are doing that, then we also log that error in the same transaction. Next, we will create our rate limit middleware, rate limit.go. This is going to be Go Boilerplate. Now this is pretty simple. We are initializing our struct here, the rate limit middleware struct, which has an embedded server. Then we are creating a receiver function, which takes an endpoint, the path of the request that the client is trying to access. Then we are checking whether we have our New Relic integration enabled or not. If it is enabled, then when we hit our rate limit, we are just logging an event, basically recording an event. The event name is rate limit hit and the data is the endpoint that we are trying to access. And we'll call this particular function in our rate limit middleware when we finally initialize our router instance. That's pretty much all about rate limiting. Then what's due is the global middlewares. Let's say, so let's create a file called global.go and let's paste all the content. These are going to be different. For this to work, we also have to create another package for dealing with our database based errors. And the name of that will be SQL error. And we have already created a folder for that SQL error. We just have to add the content. And the first thing is error.go. And here we'll store all the different database errors that we usually face. There is nothing to understand here. This is all taken from the PGX database driver implementations. So we are declaring a few variables. What are the different types of errors our PGX driver can give us? It can be a not null, can be a foreign key violation, a unique key violation, or a transaction failed, or too many connections. These are the different kinds of errors we can expect from our database driver. Then what this function is doing, our database driver is not going to give us errors in this format. It is going to give us errors in number format. So we are just taking our code, the number, and we are converting it into a readable string so that we can process it later and we can log things, and it is more readable that way. Then we also have a severity map. What is the severity of the error we want to log? Then we also have a function which takes a string, which in this format, error, fatal, panic, and it converts it into an appropriate variable of type severity. Then down here we have a couple of utility functions which we might or might not use later on, but just kept it here just in case we need it in the future. Then finally we have our handler, which is going to process different types of database. Now this is a lot of custom code that I have written over the last 2 years. I'll try to explain it as much as possible, but understanding all of it, how it actually works, is a little complicated, and we'll only get it once we start dealing with database errors. So for now, I'll just explain the implementations, but don't try to understand completely. We'll understand it once we are actually building projects using these modules. So this is the function that we actually care about, which takes a variable called error, and the type is error. At first, we check if it is our custom error type. And if it is, we just return that error. We don't try to do anything else with that error because we already know what kind of error that is. But if it is of type error, the error type which is coming from our own database driver, then you want to handle it, because this whole handle error function, it exists just to deal with our database driver based errors. And there are a lot of automations here so that while we are trying to execute different database query, we can handle pretty much all the use cases. For example, let's say we have a table called to-dos, and when we run a select statement, select star from to-dos. So if we have not created any to-do, the table is empty, then our database driver, instead of returning an empty array, it returns an error, and the error type is no rows. So in that kind of scenario, we don't explicitly handle a case where if it is no rows, we want to return an empty array or an empty slice. Then our front end will end up seeing a 500 internal server error instead of just getting a 200 response with an empty array. So there are a lot of interactions like that. Over time, as I noticed more and more errors, I have tried to generalize all of them using a couple of utility functions. And it takes a particular database error type, it parses it and tries to understand it. And depending on the type of the database error, it tries to create a message, our own custom error format, so that we can send that to our front end or to our client, which has more user readable and meaningful information. Okay. So the whole point of this file is taking a database error, a cryptic database error, and converting it into a user readable message. So at this point, what we do, we call this function, which is convert PG error. What it does, it takes a database error, a database driver error type, and it converts it into this particular error format, which has the code, the severity, the database code, the message, schema name, table name, column name, database name, constraint name, or the driver error. Right. Now going back, we also try to generate the error code, which is another function which basically checks for some error codes and returns us a strings like record, not found, already exists, required, invalid, etc. Then we are creating a user-friendly message, which is this function, which takes our SQL error, which has all the data about the code, the table name, the constraint it violated, and everything, all the data we need to create a message. Then depending on the code, if it is a foreign key violation, we say something like the referenced value does not exist. If it is a unique violation, then we say that this particular value already exists in our table. If it is a not null violation, then we say that this particular field is required, so you have to pass it. If it is a check violation, then we say that this fails our validation error. If we cannot find any of these from the code, then we return a generic response, which is an error occurred while processing your request. Now, finally, depending on the code, we decide what kind of HTTP error message we want to return. For example, if it is a foreign key violation, the user has sent some kind of data which is not valid. In that case, we know that it is a bad request error. So that's the error type we return with all the user message, readable user message, and a error code. Similarly, if it is a unique violation, the user has, let's say we are giving the user the ability to create a username, and the user has created a username, but that username already exists in our database. In that case also, we return a new bad request error, right? Which is of type 400. Same way, if it is a not null violation, a field is required, but the user has not passed it. In that case, we also request a bad request error, but we provide the information about the field. This particular field is required, and this is the error message. Same way for check violation, we also return a bad request error. If we cannot find an appropriate error to send to the front end, finally we return a new internal server error, which basically means that this error is on us. We messed up. It's not on the client. And finally, this case, if it is of type error no rows, which I said, if you have a table and it does not have any data and you run a select star query on it, it returns an error which is of type error no rows. And the reason we have added this particular case in the end without all this formatting is, if we have error no rows type of error, then we don't really get more metadata information like the table name and etc. That's the reason we are doing some custom handling. I'll show what exactly this logic does when we finally write a database query, but it basically takes our user written error message and it tries to parse the table name from it, and then it returns a new not found error, which is the resource not found. In the end, if we cannot do anything else, we just return a new internal server error. That's all about database error handling. Now let's go back to our global error handler. Since we have this package defined now, we can proceed to our other middlewares. First, we are creating a struct which is called global middlewares. Inside that, we are passing again embedding our server. First, we are declaring a coarse middleware. Now, if you are not familiar with coarse, we need a coarse middleware so that our server can add some headers, some useful headers, which is going to be needed by our web browser. If we are running a front-end application which is going to communicate with our server, then our server needs to send a couple of headers in the response so that the browser knows this particular origin is allowed. That's the use of the coarse middleware. You can read more about that. Then we have a very important middleware which is called the request logger. And the whole purpose of this is a middleware which basically logs every single request that hits our application, and it tries to log everything. The path the request is trying to access, how much time it took, and the IP address of the request, and the user agent of the request, and all the things surrounding that request. It logs everything so that we have a understanding of how many requests you are hitting and what are the different types of requests, whether we are returning success messages for that or whether we are returning error messages for that, and all these different kinds of information. So this is basically a middleware, and we are using a inbuilt middleware which is provided by Echo only for logging our requests. It has a lot of customization options, but here what we are doing, we are just trying to understand what kind of error response that our handler has returned for this particular request, and depending on that we are logging accordingly. If it is an error response, so something like 500, then we are making it as error. If it is something like 400, then we are just adding it as a warned level. Otherwise, we are making it as an info level. Then we are adding our request ID and user ID to the log so that this log is connected to our traces. That's our request logger middleware. Then we also need a recover middleware. Now, recover middleware basically is a safety net for us. So if you have watched the complete Go basics video, there I have explained that in our whole request response lifecycle, when our server is processing hundreds of requests and it is sending hundreds of responses for those, if some request is not handling an error properly and that error causes a panic. Panic basically means the most critical type of error, which is going to stop our server, which is going to crash our server. If an error like that occurs during the request processing lifecycle of our server, and if we don't have a recover middleware configured, what happens? Our server crashes. Since our server, the main process, is the main go routine, and all the other requests are spun from the main go routine. So this is a safety net, so that whenever a panic occurs during our request lifecycle, what it does, it recovers from that panic and it converts that particular error into an internal server error, and it sends that error message back to our client. But it does not really crash our server. It catches the error before it reaches our final main go routine. So that's the use of this middleware, which is very important middleware. And then we also using the secure middleware. This basically adds some of the recommended security headers to our responses. Then finally, we have our global error handler. Now, the whole point of having a global error handler is no matter what kind of error occurs and where it occurs, all the errors finally reach this global error handler. And at this point, we can decide what we want to do with this particular type of error, and we can send a nicely formatted error message back to our client, back to our front end. So what we are doing here, we are taking the error, whatever error that occurred, does not matter where it occurred, but it will finally reach this global error handler. And we also have access to the context. Okay, we are taking the original error, and then we are checking if this particular error is of type HTTP error or not. If this particular error is of our custom error type or not. If it is not, we can check this using errors.as. If it is not, then we are checking if it is of type echo error. So the library echo, the framework that we are using, that also has its own custom error type. Then we are checking if it is of echoes error or not. If it is of type echoes error, then we are checking if the status code is 404. So most likely, because we are already handling 99% of the errors ourselves by converting it to our own custom error type. So only one case remains where it can be of type echo error, basically of this type, which is if a user tried to send a request to a route, to a path which does not really exist. So we are handling that at this point by sending a not found error with the message that route not found. If it is not of type echo error, then we can say that this is not of type HTTP error, this is not of type echo error. Then the only possibility remains is it is of type database error. And for that, we have created another function called handle error, which we just saw in the SQL error package, which is going to take the error of our database driver, and it is going to send a nicely formatted message back to our client. Okay. Finally, this is all the alternative conditions. If it is of type that we have configured ourselves, our custom error type, then we perform some operations. We take different fields and assign it to all the respective fields for that particular struct, and we log the error by taking out the logger from our context, and we send the error final response back to our client with all these different fields: code, message, status, override, errors, action, whatever custom fields that we have configured for our custom error type. Right? Now that's pretty much all the middlewares that we are going to make use of in our application. So finally, now that we have all the middlewares ready, we have to create a struct which is going to contain all these middlewares in a single struct. So for that, let's create a file called middlewares which is going to be a single struct, and we are going to embed all the other middlewares here. It's the global, auth, context enhancer, tracing, and rate limiting. And at this point, we are just fetching our new Relic application from our server, and we are embedding it into the middleware, and we are passing it inside the tracing middleware since we have a dependency on that. And this whole pattern is called dependency injection, in case you missed it earlier when I mentioned it. Now that we have our final middleware struct, we can make use of this in our routing setup. So next, we can go ahead and create our service implementation for adding all our services. So let's go to service and create a file called services, which is going to contain all the different types of services. We don't have any services yet. So since this is a boilerplate, the only thing I can think of is the auth service, auth.go. This will basically have the initialization code for our Clerk service by passing the secret key that we got when you registered for Clerk. You can follow the Clerk documentation for getting your secret key, and you can add it in your environment variable. And this is what it is going to look like. We are creating a new struct which is called auth service, and this is the initialization code for auth service, which is basically we are taking out the secret key from our config, and we are initializing the auth service and returning it. And in our services file, we can create a new struct, which is, say, services struct. And first thing it will have is the auth service. And the second thing it can have is the job service. This is basically the background job service that we created earlier. And after that, we also need the initialization code. This is going to be the initialization code. We are going to pass a server instance and a repository instance, and we are going to return a services instance. A repository you have not created yet, so let's go ahead and create a repository file, repos. Again, this file will contain a struct which is going to embed all the other repository instances. But since this is a boilerplate, we don't have any other repository. Is basically we'll have different database methods. So we can just keep an empty struct so that we can satisfy our service dependency. This is what the code can look like. We are creating a new struct called repositories, and this is the initialization function. Now going back to our service file, we can import that. We'll take the repositories struct as a dependency, and we can pass that dependency to different services. For example, if we have a to-do service, which is going to deal with all the to-do APIs, then what you can do, you can pass repos.todo, the repository instance of to-dos, to to-do service, so that the whole dependency injection workflow works exactly the way we want it to. Now, finally, we can go ahead and implement our final router, which is going to initialize all the middlewares and all the system routes with appropriate grouping. So let's go to router folder and create a new file called router.go. This is the code of initializing our router instance is going to look like, but it has one error because it has a dependency on our handler instance. So let's go ahead and create that first. Going back to handlers, let's create a new file called handlers.go, and this will again have one struct which is going to contain all the other handlers because of the dependency injection pattern. So I have created an empty struct which is called handlers, and a initializer function which for new handlers is going to return a pointer to the handler struct. Now we can import that here. And another error here is register system routes. We need this particular function so that we can register different routes for our own internal use. I'll show you what those routes are and what are the handlers for those. But first we need to create handlers for those routes. So let's go back to our handler module and finish the work there and come back to our routing module. So for handlers, there is one important abstraction that we need to create, is the base.go file. Now this code is going to look very complicated, and initially when I was working with Go backends, I noticed a lot of boilerplate, and everyone eventually abstracts out all the boilerplates in their own way. So after months of experimentation and looking at what pattern works for me, I have written this way of abstraction where we can write all the code for initializing our DTOs and performing validations, logging our requests, and returning appropriate responses. All of them in a single function so that we can reuse that function in every single handler instead of writing all the code ourselves. So I'll just paste the whole implementation here and explain it. but you don't have to understand the implementation. As long as you know how to use it, that's more than enough. You'll eventually get what we are doing as you get more comfortable with the language. So this is what the implementation is going to look like. Again, we have a dependency here on the validation package. So we actually have to go back and implement the validation first before we can come back and implement the handlers. It will have two files. The first one is going to be, let's say, utils.go, and this will contain all the logic that we need to perform validation and to return appropriate responses, the form errors, and everything related to validation. And this is what it looks like. We have implemented an interface here so that whatever struct, whatever data type inside our whole application, which has a receiver method named validate, that will satisfy our interface. Since we already know that Go has this implicit interface implementation, that whatever data type implements this method will by default satisfy this interface. And this is very important as we write our DTOs, our data transfer objects, which we are going to validate. We will have to implement a validate method on top of those DTOs so that we can actually run our validation logic on those structs. Then we are defining a type called custom validation error, which will have a field, the name of the field, and the message. And this is a slice of custom validation errors. And we are defining a method called error on top of custom validation errors so that it satisfies the error interface. Whichever data type in Go implement this error method, by default, it will satisfy the error interface and it can be used in place of errors. Then we have a method called bind and validate. What this does, it uses the bind function provided by the framework we are using. This is one of the reasons we are using the framework, so that we don't have to write our own binding logic by unmarshalling the body into our struct and validating it and all the different things. We can just call one function and get rid of all the boilerplates. So first, what we are doing, we are trying to bind whatever query parameters, whatever payloads that is coming in our request, and we are trying to load it inside our payload. Right? If we face any errors during that, we return a new bad request error, which is of type 400. Again, the next step, once we have successfully executed the binding logic, binding is basically the deserialization logic. Since data travels in the internet in the form of bytes and bits, we take the bytes that we received in our request and we try to deserialize it into our Go's native data type format. That's what we are doing here. After we have a struct, a native data type of Go, then we can take that data type and we can actually validate it against a set of rules. Rules like a string should have minimum this number of characters, and the type of an ID should be UUID, and other validation logic that we have written elsewhere. Second thing, what we are doing, we are taking that payload where we have deserialized our bytes into a native Go format, a struct. Then we are running this validate struct function on top of that. If we get any errors while doing it, we return a new bad request error with all those errors so that the user can see them and fix them. And if we take a look at this function that we are calling inside bind and validate, this function does not really do much. What it does, it takes a data type which implements this interface, which is validatable. And what we are expecting a data type which has a method called validate, so that we take that interface, a data type which implements a validate method, then we call that method on top of that data type. And while calling it, if we get any errors, what we do, we call this function, which is extract validation errors. If we get any errors while we are validating, we want to extract those errors properly so that we can send that to the user. Now coming back to this function, the final function in our validation pipeline, what it does a couple of things. Mostly it implements our own custom logic. So first, what you're doing, we are declaring a slice of field errors. Field errors, as I have explained before, field errors are basically all the form based errors. If you have a form for name, username, email, password, then if one of those fields has some errors, then we send a slice of field errors so that the front end can accurately validate the request and can fix those errors. So what we are trying to do here, we are checking if the error that we got, if it is of type validation error, which is coming from the library that we are using, the validator library, the package. We are checking if the error type is from the package's error type, the custom error type of the validator package. If it is not, that means that the error that we got is of our type that we have implemented, which is the custom validation errors. Then we again check if the error that we got is of type custom validation errors. If it is, what we do, we loop through all the custom validation errors and we append it into the field errors slice. Then this is the case for when we get custom validation errors, especially for form-based interfaces. Then if it is of type validation errors, which is the data type, which is the error type of the validation package, here we are just switching through, then we come inside this. We are taking the name of the field on which struct field exactly we got the error. Then we are declaring a variable called message. In this variable, we'll store the final message, the message that we want to send to the user. Then we are switching through the tag. Now, as I said, in Go, we can use struct tags to provide different conditions, different rules, different configs. So if we go to our config package, you can see that inside validate, we have written required. Now, when we call this function called tag, it will return us whatever value that we have passed inside this struct tag. So since we have passed required here, if we call tag on top of this field, it should return us required. That's what we are doing here. We are switching through whatever tag that is defined for that validation, which basically means that what validation rule that we are trying to apply here. If it is required, then the message is required. So we take the name of the field, which is, let's say, address. And if the tag is required, then the final message will be address is required. Same way, if the tag is minimum, then we check if the type is string. If it is of type string, then the final message that we are writing must be at least this number of characters. If it is not string, then it can be, let's say, a number or a slice with a minimum number of elements. So in that case, we don't write characters, we just say must be at least this. Similarly, for max, we do the same kind of logic. Then becomes one of. One of basically is kind of a enum. It has to be a one of a certain number of values. So if we are taking a field called status, so in status, the user can only pass pending, success, or archived, things like that. So any kind of enum scenarios, we use the tag one of. And in that case, we are returning the message that must be one of these values. For email, we are saying must be a valid email address. For E164, it means that it should be a valid phone number with country code. For UUID, we are saying must be a valid UUID. For UUID list, basically means it should be a comma separated list of UUID. Div means if you want to validate an array, all the elements of an array. In that case, if we get some error, we can just say that some items are invalid. Finally, in default case, we are building some default message using the field name, the tag, and the parameter that is passed. After everything, we take the message that we just constructed using this switch statement. We pass that message as error, and inside field, we take the field name. And finally, we say that validation failed, and we pass the field errors as the value of the errors. That's what this whole extract validation errors thing does. It returns it to validate struct, and now validate struct returns it to here, which again passes all these field errors to new bad request error. And if we go inside new bad request error, the fourth parameter is the field error, which again passes it in the errors field. So that is our complete validation pipeline. We will see how the validation works when we are actually building the projects, but this is all the setup that we need for the whole workflow of automating our validations. Okay, great. Now that we have implemented our validation, we can go back to our handle logic. This was our base handler. Now, what's happening here? We are declaring a struct called handler, and we are embedding our server inside it. And this is the initialization function for that handler. So instead of going line by line here, and explaining what is exactly happening, let me just explain what we are trying to achieve in this file. Why have we created this file? Why have we created this abstraction? So it has a couple of functions. Let's say handle. In most of the handlers, what we do, we call handle this function, which is a generic function. Generic basically means you can dynamically customize the type of your function. So we take two type parameters for request and for response, and the request payload, whatever that we pass, should be a data type which passes the validatable interface, right? And we take four parameters. The first one is the handler, an instance of the handler struct. Then inside the handler variable, we have the handler function, the function that we actually want to execute when this handler runs. The status, what is the status that we want to return after this handler successfully executes. Then the request, the payload that we want to validate, right? Then it returns a function by executing this function, which is the handle request. And if we go inside this, handle request does all the abstractions that we want it to do. First, it starts a timer so that we can actually measure how much time it took to process this whole handle logic. Then the method, the path, and the route. Then we are taking out the transaction that we had embedded inside our context for New Relic integration so that we can add a couple of attributes to this particular transaction. As I said, the whole point of transaction is during our whole request lifecycle, we want to keep track of what did a particular transaction touch exactly. What are all the functions? That's why we are adding the attributes here. Then we are creating a new logger for this particular operation, this method, this path, and this route. Then we are taking out the user ID and adding that also to the transaction. Then we are starting another timer to keep track of how much time exactly our validation took. Then we are running this whole bind and validate function so that we bind, we deserialize it into a Go struct. Then we run all the validation rules on top of that struct. If we face any errors, we add that to our transaction, our New Relic transaction, and we return the error from here, and that gets converted into an appropriate format in our global error handler. But if we did not face any errors, we come here, we measure how much time it took for the validation, and we add that in the same transaction. It took this much time to perform validation for this particular request. Then we are logging some debug information, starting another timer, and then we are finally executing the handler that we pass into this generic function. And whatever result we get, we store it inside this variable. But if it is an error when we executed this particular handler, we log that error and return the error. And finally, we are recording some successful metrics so that we can see it in our New Relic dashboard. We are logging some information and finally returning the result. Same way, if we want to handle a file request, let's say a user uploads a file. So for that, we need a different workflow. That's what we are doing in this function. Same way for if we want to return 204, which is no content, then we are using this function for that. And there is a reason I don't want to go line by line for this particular file, because it took me almost months of different iterations until I found a solution that I was finally satisfied with. But trying to explain it will just make it even more complicated than it actually is. So once you have used it a couple of times and go through the code a couple of times, and maybe if you want, you can pass it to some LLM, Claude, or whatever LLM that you use, and you can ask it to explain it in your own format. But me trying to explain it will just make it even more complicated. So we'll keep it at this, and we'll just understand how we can actually use this handler pattern, right? Now that we have our base handler, let's create some of our system handlers. The first thing that we need is health handler. What exactly is a health handler? Our backend system needs to expose some endpoints so that external systems, if you have Kubernetes or if you are using any other tool to monitor your uptime, etc., a lot of other external tools, they need to have access to a particular endpoint in your backend, and that endpoint needs to return a successful response. so that those external tools know that your service is running fine. And that kind of handlers are called health handlers or health check handlers. And that's what we are going to implement first, our very first handler. This is what our health check handler looks like. We are creating a struct called health handler and we are embedding our base handler inside it. Then we are initializing that struct. Even though we don't really need our base handler in the health handler because this is not a handler that deals with our business logic, but still just to keep the pattern consistent, we have embedded it here. Now, this particular struct health handler has a method called check health, which actually checks the status of our system and returns a successful response. First, we start a timer, take out the middleware that we have inserted in our context. Then we create a response format. The status says healthy. The timestamp is the current timestamp, which is time.now, and the format is UTC. The environment we take from our config and we return a map, which the field name is checks. And what exactly are we checking? We are checking two things. One is database connectivity and second is Redis connectivity. So in our health handler, in our health check handler, our status handler, we also want to give out information about our database health, database connectivity health, and Redis connectivity health. So we are starting a new context and a new timer for checking our database connectivity. And we already know that our database driver provides a function called ping, using which we can create a new connection with our database and we can check if that is successful or not. If it returns an error, then we reach in this phase and we make the status as unhealthy for the database key inside our checks, which is a map. The response time we measure from DB start up until here. Then we share what exactly went wrong with our database. Then we make the is healthy parameter to false. We log the error and we also add this to our new Relic integration as a custom event. But if we were able to connect to our database successfully, then we keep the status as healthy and add the response time starting from DB start up until here. And we log a successful response and move on to our Redis connectivity. And we do the same thing with our Redis. We check if the connection did not work, we return as unhealthy, log the error as a custom event in our new Relic integration. If we are able to successfully connect to our Redis instance, we log that and we also make the status as healthy. Finally, we check here that if either our database or Redis was not able to connect successfully, the is healthy parameter, the is healthy variable will obviously be false. That's why we are making the main response. The primary health response is unhealthy. We are logging a warning. We are recording another custom event for health check error in our new Relic integration, and we are returning that response. But if it is healthy, then we reach here. We log an info that all the health checks are passed, and we finally return a response. But while returning the response, if we face another error, then we log that also with our new Relic integration. And that's all about our health handler. Once we have a handler, we come here, and this we will do every time we create a new handler. We come here, we add that as a health handler, also as a new health. This is the pattern we are going to follow. Let's say we are working on a to-do application. The first handler that we can think of is the to-do handler. Then we can also create a comment handler. We can also create a category handler. All of those handlers will be embedded inside this struct and will be initialized in this function. On top of this, we also need another handler so that we can serve a UI so that we can test our APIs. I'll show what that UI looks like later, but for now, let's create a handler called Open API. And this is going to be the content. We create a new struct called OpenAPI handler. We embed the base handler inside it. And it has a method called serve OpenAPI UI. And for this, we are trying to read a HTML file from our static folder. We have a folder called static, but we don't really have an HTML file. So for that, let's create an HTML file called openapi.html. And this is going to be the content of our HTML file. And what it is doing, it is basically fetching all the JavaScript from a CDN, and we are making use of this service called Scalar. So if we look up Scalar, Scalar testing. This is Scalar. So this is a modern alternative to Swagger UI. If you have used Swagger UI before, you know that the whole interface, the whole UI looks a little outdated. It works, but it has a very outdated look. So Scalar is kind of a modern alternative with modern designs and modern features. So we are creating an HTML file and we are fetching the JavaScript that we need from a CDN, and we are taking a file called openapi.json, which we are going to keep inside static, and we are serving it in this HTML file. That's what this particular handler is doing. If you go back to OpenAPI handler, what is it doing? It is reading this particular openapi.html file. We are saying that we don't want to cache it. If we face any errors, we return it. Then we are converting the whole bytes into string. Then we are serving it as an HTML using echoes.html function. Right? And that's OpenAPI handler. So let's go back here and also add OpenAPI handler in this grid. Now our handler implementation is complete. Finally, we can go back to our router and create this function called register system routes. System routes are basically the health check handler that we created and the OpenAPI handler that we created. Now inside router, let's create a new file called system, and we are going to keep these three handlers here. The first one is obviously our health check handler that we have created just now. Second one, in the docs route, we are serving our OpenAPI UI, and we have another route which is static. So we are using the echoes static method for serving whatever content that we have inside our static folder. We are serving them as static files over our server. That's all the system routes that we need as of now. Now going back to our router.go file, all the implementations are complete. There are no errors. Now we can see what we are doing here. First, we are just initializing our middlewares. Then we are creating a new router instance using echo.new. We are registering the global error handler that we created previously inside our echoes HTTP error handler. Next, we are using router.use, which takes a chain of middlewares and it will implement those middlewares in that order. The first point of contact, the first middleware that we are going to touch is this one, the rate limiter. And we are just using the echoes default rate limiting middleware that comes from the echo package. We are saying that we just want to maintain whatever rate limiting related details inside our memory. We can definitely make use of Redis, which we will probably in the future. But just for the sake of implementation, we are using the in-memory store. Then what happens when we actually hit the rate limit? When we actually hit the rate limit, we are using this function called record rate limit hit, which basically uses our New Relic integration for logging that, and we can monitor that and set alerts using that in our New Relic dashboard. Then it logs another warning, and finally it returns a 429 response to the client, which says that too many requests and you can try again later. That's the first middleware. Second, we are registering the CORS middleware. Third, the security middleware, all the security headers that we add in our responses. Next, the request ID middleware, which basically checks for a request ID if it is coming from the load balancer. If it is not, then it creates a new request ID using UUID package and it adds it into the context. Next, we are adding the New Relic middleware, which keep tracks of different metrics and connectivity and all other logging, monitoring, and observability data. Next up, enhanced tracing related data, things like span ID, etc. into our context. Then this middleware basically enhance context. It creates a transaction using New Relic transaction and it adds that also to our context. Finally, we have our request logger, which basically logs all our requests, and the recover middleware, which helps us recover from panic and helps us avoid crashing our main go routine. After we use all our middlewares here, finally, we are registering our system routes, which is the OpenAPI handler, our health check handler, and our static handler. Then we are creating a new route group, is /v1. We don't have any routes for our business logic yet, but this is a boilerplate. So next time we create a project, we'll be starting from this point and we'll be adding all our business route after this. And that completes our router implementation. Next, I have created some files for all our testing needs. These are some functions which are going to help us with the assertions that we are going to use repeatedly while we write our tests. And this is the actual implementation of containers using our test containers for a Postgres database. Then there are some helpers here so that we can set up a new test and perform database cleanup and some of the utility functions. Here we have a function that creates a server for our testing workflows. And here we have some utility functions for our tests. We're not going to go too deep into all these functions now. We'll understand these when we are actually writing our tests. Okay, now finally we can move on to our main.go file. We have all the other dependencies already implemented. So we'll write the final function, which is going to bring all of these together, and it is going to start our server, and it is going to start serving requests that are reaching our backend. This is what our main.go file is going to look like. First, we are defining a timeout value, which is going to be 30 seconds. First step, we load our config, which takes all the variables from our .env and loads it into a struct, which is going to be loaded inside this CFG variable. Then we take that config and we start our new Relic logging service by passing the observability related config inside this logger service. Then we finally take this logger service and pass the observability related config here, and we have our logger that we are going to use across our app. Then here what we are doing, if this is not a local environment, if we are in a prod environment or a staging environment, we are taking all the database migration files that we have written here and we are applying them, because in local we can just run a CLI tool and apply migrations, apply rollbacks, but in production everything is already tested and we just want to take all the migrations and apply them. That's what we are doing here. Next, we are starting a new HTTP server from our server package and storing it here by passing the logger service and our configs. If this fails, we just panic and crash our server. Since this is our main.go file, there is no returning any error. If anything does not work, it's a fatal error and we want to crash the server. We want to stop the process here only. Next up, we are initializing our repositories, initializing our services, and initializing our handlers. So all the things that you are seeing, this is called a dependency injection pattern. You initialize all your dependencies in one place and you pass them around as instances throughout your application instead of declaring a global variable and importing it directly. So we have initialized our repositories, services, and handlers. And also we started our router instance. We started our HTTP server by passing our router inside it. Then this part of the code is basically our graceful shutdown. What we're doing, we are listening for signals like control C or any kind of close signal. If we find any signal, what we're doing, we are giving our server 30 seconds, and under 30 seconds, it has to do all the cleanups like database cleanup, Redis cleanup, our observability service cleanup, and finally our HTTP server cleanup. And when we say graceful shutdown, what actually happens is, let's say you are in production and you are shutting down your server. All the requests that are currently getting processed, they will not drop, they will get processed. That's why we are giving it a 30 seconds of timeout, but any new request is going to get dropped. We are not taking any new requests. We are just trying to finish whatever our job is, and we are trying to make sure we clean up everything, all the resources, before we finally stop our server. And that's our final main.go file for starting our server and putting together everything that we have written so far. One piece that is still due is our environment file, the .env. We have to put all our variables here. So I'll just go ahead and paste it here and explain the structure of them. And this is what our environment variable file .env file is going to look like. This is the structure that I was talking about when we're creating our config.go file. This is our prefix, the name of our app, so that we don't clash with any other environment variables when we deploy this in a server environment where other applications are also running. After this is the name of the variable, and The first part is the name of the struct that you want to load it into, and the second part is the name of the variable, right? We have defined all the values that is suited for a local environment. So let me just take this and paste it into .env.sample, because .env is going to be git ignored and it will not get pushed into the GitHub repository. .env.sample will be pushed, so you can just copy this and create a .env file and paste it and make changes according to your own needs. So let's just go ahead and create a database and we can check if our server is running fine or not. So let me just come here. I am using Table Plus, by the way, managing my database. I'll create a new database, Boilerplate, which is the name of our app, and we'll open that. Going back, let's just say, and our server is up. You can see that our database is successfully connected. The background job server is running. That means Redis is also successfully connected. And finally, our server has started in the port 8080. Boilerplate for our Go backend. Now, one final part that is due is setting up email workflow and our OpenAPI contract generation workflow and our Zod schema workflow. So let's get into that. Then we can wrap up this video. Next up, for the packages that I had mentioned, we are going to use a couple of workflows, a couple of packages from TypeScript ecosystem. I have a lot of experience in the TypeScript ecosystem. I started as a TypeScript backend engineer. So over the years, I have a couple of my favorite workflows, and when I started working with Go, I was really missing them. So with this whole monorepo setup, I found a way to still make use of them. It does not take too much of an effort to make it all work. Okay. So first, let's take a look at how we are creating our emails or our email templates, how we are maintaining them. First, inside packages, we have a folder called emails, and inside that we have a testconfig.json file. Since it is a TypeScript package, you can explore what all this config means by looking up, but we'll not be covering that here. Then we have a package.json file. The name of the package is boilerplate/emails, and we have a description here, and the type is module, since we are going with ES modules, not common JS modules. And we have two scripts here. One script to run a server, a development server, so that we can see the preview of the emails, and a second script which basically converts all the emails into HTML and saves them inside our backend templates and emails folder, so that our backend can take those HTML file and inject data and send those emails, which we have already seen and written the code for. But now we'll see how we can create those emails. We'll be using this package called React Email. This package comes from the same team which has created Resend, the email sending service that we are using. And it is a very useful package. It offers a very modern design and a very smooth workflow. Since I come from a front-end background as a React engineer, they provide you workflows so that you can write React, you can write Tailwind, but the final generated email template will be in pure HTML and CSS. It is very convenient, since I don't like those no-code workflows that these services offer. Services like Brevo, MailChimp, or whatever email sending, email campaigning service that we use. They offer this no-code workflow where you can drag and drop different elements to create your email from scratch. That does not really feel very intuitive to me. So I like this workflow. I like being able to code every single part of my email instead of just drag and drop, right? So we'll be using React and React email package to create and maintain our emails. That's pretty much it. This is what our email template is going to look like in React code. So we are importing a couple of components. Now these components are coming from React email package. And when we actually export these emails, these components get transpiled into pure HTML and CSS, and they all follow best practices so that our email does not break and it looks perfect in mobiles, in desktops, in laptops, in all different screen sizes. It is automatically responsive and it is automatically accessible. Now in the props, we are mentioning what are the parameters that we are going to receive for this particular email template. And there is a reason we are using this particular pattern here because when we go to, let's say, what is the file client here, when we actually do template.execute, what happens, this package, this HTML template package, it looks for all the places. So let me go to the, let's just do one thing, cd into the packages /emails, sorry, I think I put an S, and let me run this export command. When we run this export script, what happens, when we go to our backend templates emails folder, a new HTML file is created. And when we take a look at this is a pure HTML CSS implementation of how a email template should look like. But the part I want you to focus here is this. This is a placeholder that we have manually injected in our React code, in our email template code, so that when our Go backend, Go HTML template package reads this HTML file, it will look for this particular placeholder, and whatever first name the user we pass in the Go code, it will replace the whole thing with the user's name. And it creates this smooth workflow between React and HTML and Go, and it just works out for me, right? It's very intuitive and very less friction. That's the reason in React code we have written the format like this. Next up, it's just normal React code. If you are not from a front-end background, this might look a little complicated, but again, you can take the help of any LLM. Since this is pretty basic, you can take the help of V0 to generate these kinds of templates. But if you don't like this workflow at all, writing this code for generating your email template, then of course you can go for those no-code solutions that these email providers offer. Providers like Brevo, MailChimp, and whatever we have, Postmark, right? And we have wrapped the whole thing in Tailwind so that we can use Tailwind classes, and that will be converted to raw CSS in the final HTML format, as we can see here, all these classes. Okay. And there is not much here. Apart from that, we have a very basic template, and we are providing some preview props so that when we start the development environment for our email, we can see what the first name is going to look like. So let's just do that first. We can hit a new terminal and let me just run bun. Now, when I ran bun dev in the root of our project, it actually went into the package.json and it used this command, which is turbo run dev. And what turbo run dev does, it goes through the package.json of each of our packages. So for this, we have a dev command. For this, we have a dev command. And for our emails package, we have a dev command. It starts the dev server for all our packages. And this is very convenient. With one single command, you can start the development server instead of seeding into every packages and manually starting the development server. Anyway, since we have started the development server of our emails, let's just go ahead into this link. This is our development server. And if we click, let me just move this so that you can see how this looks like, right? When we click on welcome, you can see this. We have a preview of our email. Move it back. This is what our email is going to look like. This is very convenient. You already know what is your email going to look like in mobile phone, in desktops, in laptops, etc. And you can develop your templates accordingly. That's pretty much all about how our email generation flow is going to look like. The next part is one of my favorite parts, which is the Open API contract generation workflow. For that, we are using a couple of integrations. So the first thing is we have a Zod package. We have again a tsconfig.json file with appropriate configs. Then we have a package.json file. The name of the package is Boilerplate Zod, and this package will be imported into the OpenAPI package using this name. Since we are using a monorepo with workspaces, we can import internally other packages inside other packages. We have 3 scripts here again, one to build this, one for starting the development server, and one to clean it. And we are exporting whatever we have inside index.js from here. And We have installed a couple of packages. One is this Zod Open API, which provides some good integrations on top of Zod using some metadata. And we also have Zod. Zod is basically a validation library in TypeScript ecosystem, and it has first-class support for JSON schema. JSON schema is again used in OpenAPI.json. That's why it's a very clean, a very smooth integration. I'll show how that works. So next, we have a utils file, which we are going to use later on when we build responses which have paginated response. Second, we have an index.ts file where we are just exporting everything from. Then finally, we have a schema file. Here we are declaring a Zod schema, and this schema is exactly the response type of our health check handler. So if we go to our health check handler, let's just keep it on the side, and here I'll open the health check. So this is our health check handler. And as you can see, we have the one-to-one mapping from our Go-based response and our Zod schema. And this is important. This is important because when we finally build our type-safe API client using TS REST, or when we are generating our OpenAPI schema using TS REST, the typing has to match. So this is the only effort that we have to put manually. Everything else is automated. And as compared to the comment-based approach using libraries like Swaggo in the Go ecosystem, I like this much better. So we have a status field, which is a enum type. It can be healthy or unhealthy. Then we have a timestamp, which is of type datetime. Then we have environment. It can be a string. Then we have checks, which is an object. Inside that, we have a database object and a Redis object. For both of them, this is the same schema, which is status, which can be either healthy or unhealthy. What is the response time it took to connect to the database or the Redis? And if there is an error, what is that error? And this is the return type of our health check handler. And we have recorded that as a Zod schema. Okay. Now, when we are developing our backend, for example, if we are building a to-do application, so we'll create a file called todo.ts. We'll record all our backend models as Zod schemas in that file and export them. This is going to be the source of truth for our OpenAPI and our type-safe front-end client generation. That's all about the Zod packets. And finally, we have the OpenAPI package where we are maintaining and generating our OpenAPI contract. Again, we have a package.json file with the name of the package and a couple of scripts. This gen script is for generating the OpenAPI.json file, and the dev script is for when we are running the development server. Again, it exports the contract so that in our front-end code base, we don't have a front-end code base yet, but when we do, we can import this contract and generate a completely type-safe client, which is very useful if you have worked with front-end code bases before. Then we have installed TS REST, which is going to be the library that we use for writing our OpenAPI contracts and generating the final OpenAPI.json file. Then inside SRC, we have a couple of files. There is a utils.ts file where we are exporting the security related, since we are using bearer token workflow for our authentication needs. We are exporting that from here. Then we have a gen.ts file, and this is the logic that we are using for generating our OpenAPI.json file. Don't have to understand it. You can just copy paste and use it all the time. This is not a function where you need to make changes frequently. Then we have the final index.ts file where we are using some of the functions provided by TS REST, for example, the generate OpenAPI, etc. And finally, we are adding some metadata about the security schemes, the name of our application, the version, and what is the URL of our server. Some of the metadata about our server. And finally, inside our contracts, we define all the contracts that we need and that should be converted into a OpenAPI.json file. So index.ts is basically the place where we merge all our contracts into a single file and export from there. And there are other files in this folder where we actually define the contracts. Since we only have a single handler, which is the health handler, we are defining the contract for that here. So what it does, this is the name of the operation, which is the operation ID. Get health is the summary field which gets populated into the OpenAPI.json. Same way, this is the path, this is the method, the description of the whole operation, and the type of the response. All these things are used to generate the final OpenAPI.json file. So let's just go ahead and I'll just cd packages / OpenAPI, and let's just run the bun gen command. What it does, it executes this particular file and generates an OpenAPI.json file. One version is written inside this package, OpenAPI package. This is the completely generated OpenAPI.json file, and another version is written inside our backend static folder, which our backend will take and host it in the /docs endpoint. So now if we start our backend server and we go to this particular port, here we have our UI, which comes from Scalar, a modern alternative to Swagger. So if we come to this endpoint, the endpoint that we just defined, get health endpoint, we can see we already have the response type, which is the exact response type that we are expecting. And it only happened because if we check here in the Zord package, inside src, inside health, we have declared this schema, this Zord schema, and we are importing this schema inside our OpenAPI contract from here, since this is a monorepo, and we are providing that as a response to here. That's why we can see the complete schema, what our response is going to look like. Now, if you go to test request and send it, this is the response of our health check. It is returning the environment as local. The status is healthy, since we are successfully able to connect to both to our database and Redis. This is the timestamp, the current timestamp, and says that this is the response time. This is the 8 milliseconds for our database and 3 milliseconds for our Redis. So using this whole TypeScript ecosystem based OpenAPI contract generation, we don't have to write those ugly comments on top of every single handler in our Go code. We can keep our Go code clean, but on one condition, that we have to maintain a single source of truth in our Zord schema and inside our OpenAPI contract. The contract format, as you can see, is not very long. In fact, it is more readable as compared to the comment-based OpenAPI.json generation. And we'll also see in the future, this particular workflow also gives us a complete type-safe client, which we can use in our React TypeScript code to get autocomplete and all the type-safe niceties inside VS Code. I think I also forgot one last thing, which is implementing our base models. So let's just do that and we can wrap this up. Let's create a file called base.go, and inside this we'll keep a couple of structs and data types, which we will be reusing across all our models when we actually create our database tables and map those tables in our Go structs as models. We'll be reusing these. Basically, utility structs. We have a base struct which has the ID and created it and updated it field. But if we only want the ID field, we can use base with ID. If you only want created it, we can use this. If you only want updated it, we can use this. If you want only 2 of this, then we can use 2 of this. And we also have a struct for our pagination based response. And we are going to use this base model in all of our database models. And with that, we have completely finished our Go boilerplate. This boilerplate is going to be the starting point in all our future projects, so that all this 3-4 hours of explanation we can completely skip and directly write our business logic, build features, build really interesting features, and learn more things instead of focusing on the boilerplate. That is the whole point of making this video. It is a one-time effort, and I'll be pushing all of this code that we have written today into a GitHub repository, and it'll be a public repository. So every time you're starting a new project, you can just clone it and start from there. And whatever customizations that you want to do on top of this code base, you can do, obviously, since it's not necessary that everyone will like this particular structure or this particular way of organizing code. But I feel this is a very good starting point for any kind of small to medium scale projects. So that's all about this video. In the next video, we'll be actually using this boilerplate to build a production grade project.